Hey everyone, today we are going to go ahead and do a implementation of the Llama4 architecture. So Llama4 just came out, and I think it'd be helpful just to see exactly what's going on, understand a little bit of the inner workings. So just as a couple of caveats going into this video. The first one is all of the code is basically what came from the Huggingface repository in their Llama4 implementation. So let me pull that up real quick. So they obviously get full credit for all this code. You can imagine what we're about to do is kind of just a annotated walkthrough of what's going on and trying to understand exactly how Llama4 works. So again, they get full credit for this code. I tried to keep it as similar as I could to this, and I just added in lots of commentary, if you go check my Git repo, about exactly what's going on at every single step. So we're going to get to the code in a bit, but there are actually a couple other caveats that I want you to keep in mind. The first major caveat is I am already assuming that you know what transformers are, what mixture of experts are, what KV caching is, and what rotary embeddings are, and a couple of other little things here and there. I'm going to do my best to try to explain exactly what's happening, but this video would end up being way too long because there's actually a lot of code to write. Granted, there's great resources for this stuff online. I think I'm putting the cart before, the horse here, because I was planning on doing this video later after I had done my individual kind of videos on what is mixture of experts, what is KV caching, what is rotary embedding, all that sort of stuff. But then Llama4 just dropped. And I'm like, well, I might as well just implement it and kind of present it to a more advanced user, let's just say. So people that have a little bit more experience. And so, yeah, that's kind of the target audience here. Of course, if you're new to this, try to follow along. You'll probably still get a lot out of it. I'll again, try to explain as much as I can, but there's only so much I can do in a single video. The other caveat, and the toughest part, is these models are ridiculously big. As you can see, Llama4 Scout, the smallest model, is still over 100 billion parameters. Maverick is 400 billion parameters, and Behemoth, which they haven't released yet, but I'm sure they will soon, is 2 trillion parameters. So I went ahead and downloaded the Llama4 Scout weights from Hugging Face, and it's about 200-ish gigabytes of just weights. And I do not have a computer that can load that. I'm sure local Llama or others will come up with some efficient way of actually running this stuff, or there might be a distilled version of this model coming soon. It's kind of sad to see our 7 billion parameter models kind of just disappear to these insanely large ones. So writing a legitimate inference script to generate text is kind of out of the scope here because there's just not enough resources for me to do that. You need at least an H100, which I definitely do not have. But what we can do is just do some test cases and understand the inner workings of the model and just set it up in that way, right? So use this as a learning exercise. Now, again, the caveat is because I haven't inferenced this model on my own code. I don't know if it's fully functional in the case of if you just loaded weights, it would totally just work. That's probably not true. And there's also probably features missing that might be specific to Scout or Maverick that I haven't really accounted for. But again, this is a learning guide, right? We're just doing an exploration here because I think I love Llama. I love using Llama. I use it all the time for kind of the different things that I do. And so Llama4 came out and I thought it'd be the right time to just go ahead and implement it because it's become very hot. Everyone's very excited about it. And others are upset because it's just so big. If you want to know more about Llama, I would look no further than this video by Umar Hamil. I'm sorry if I butchered your name, but this video will give you everything you need, right? So this is a great prerequisite video that I would recommend. Before you go into this, it'll go into more depth on some of those topics that I mentioned. And if you understand this, then you'll understand everything else in my video. So let's go ahead and put that away, and let's talk a little bit about Llama4 and exactly what is unique about it. So Llama4 added the main change that they added was the Mixture of Experts module. So it's kind of like this. Now, this isn't your standard Mixture of Experts. So if you again remember, the entire purpose of Mixture of Experts is in every transformer block, we have two steps, right? We have the attention mechanism, and then we have that feed-forward multi-layer perceptron. But in these feed-forward layers, basically every token inside your sentence, whatever it may be, every token gets the exact same feed-forward projection. And you would imagine that different feed-forward layers would benefit, different tokens would benefit from different types of projections. And that's exactly what this article shows. So let me pull up this picture. This is another really great article by Huggingface on the Mixture of Experts, so I'd highly recommend giving this a read. But I think this figure, I think I missed it. I think this figure is the coolest one. So you can see that different experts, so remember, every expert is going to get a different token, right? Potentially, you have to train the neural network to kind of route specific tokens to specific experts. Every expert ends up learning kind of different things. We can see layer 1 seems to specialize in verbs, layer 0 specializing in visual descriptions, and then layer 3 and 6 seems to do conjunctions and articles, and layer 2 and 6 is for punctuation, and so on and so forth. So we can see some specialization happening in these experts. Like different experts are learning to do a different type of projection on different types of tokens, which is really neat. So they went ahead and went with the Mixture of Experts model. There is another reason to use Mixture of Experts, and this is your active versus total parameters. So like I mentioned, Llama 4 has 109 billion parameters, let's say. That's across the whole model. But when we actually do a forward pass, not all 109 billion parameters are used. Only 17 billion of them, in the case of Llama 4, is actually used. And this is because in the Mixture of Experts, specific tokens will only go to specific routing, or basically specific experts. So not all the experts may actually be utilized in a forward pass. Regardless, we'll kind of see what this looks like. But yeah, I think that's enough prereqs. Let's just go ahead and start coding, because there's no better way to understand exactly what's going on than that. Let me double check that. This is, yep, you're still recording. And there we go. Okay, so to start the code, like I mentioned, we won't be writing an inference script because I don't have enough GPUs in the world to do that. And that's okay, right? We're mostly using this as a learning opportunity. Let me open up my reference code wherever I put it. 1 second. Let's just reopen it again. Llama 4 model. Here we go. Okay. So I'm going to go ahead and copy paste just this beginning part here. So another key part about Llama 4 is that it is a vision language model. So it has both a vision encoder, so for images, and it also has a text encoder. So I have here 2 config files for both of them. And again, these config files are very close to the ones you'll find in the, in the Huggingface configs, right, for modeling Llama 4. So again, they get full credit. But as you can see here, this model is super duper big. We have a huge vocabulary of about 202,000 tokens in our tokenizer. Each token is represented by an embedding dim of 5120, and they'll be projected up to 8192. And the MLPs, they'll be projected up to 16384. We have 48 of these transformer blocks stacked on top of each other. We have 40 attention heads. These will be the overall heads, and then we have 8 shared heads. So we'll kind of do the group query attention. So we'll see that in a bit. We have our head dim is fine. That's basically the embedding dim per attention head. We have a massive context size of 4096 times 32, right? So this model boasts a huge context size. Again, we're not going to be able to really test this stuff, but it's just to keep things in mind. And everything else is kind of fine. We have here, so we have 16 experts in this specific model. Llama 4 decides to use, you can see here, 16 experts in the model. And we'll have rotary embeddings, just like we'll always do. So we'll use rotary embeddings. I think these rotary embeddings, the ones I implemented, are basically the standard ones. I think the Huggingface one uses a scaled version of the rotary embeddings for like context size, scaling management, something like that. We won't be going that far because, again, we can't actually inference this model, so it's just for learning purposes. After that, we have our vision config, right? So we have our typical, actually when we do the vision config, it's going to look very similar to our vision transformer that we did in the previous video. So not too much there. But this vision transformer, or vision vision model, will have a larger image size. It expects images of size 448, a smaller patch size of 14. And I'll also use, actually, I'll talk about stuff I find interesting as I go through, but it also uses rotary embeddings and positional embeddings in its implementation. So we'll see what that looks like. So the best place to start is our mixture of experts, right? So that's kind of the key novelty or difference that we have from the previous model, Llama 3 and earlier, to Llama 4. So let's go ahead and implement our mixture of experts. Now, in this mixture of experts model, in the most efficient implementation, every token would be routed to every expert independently. So basically, you wouldn't have any overcompute. You wouldn't pass a token to an expert that it wasn't assigned to. I'm not entirely sure why Huggingface, the way that they did it, they actually just do a full dense forward pass for all the tokens through all of the different experts. Maybe they tested and saw that there wasn't all that much of a difference. I'm not actually sure. Or maybe doing that type of like specialized forward pass operations requires more custom CUDA kernels, which they didn't want to get into. Or the assumption is that when we do a lot of these operations for models this big, the different experts would be split between different GPUs, so the overhead is not as bad. I'm not entirely sure, but either way, we are going to implement it exactly how they did it, so when you go and read their code, there's less of a confusion. So let's go ahead and do our class. I'm going to call everything exactly the same as they did, right? We want to make sure we stay true to their code. Init self config. And so what we're going to do is let's do super Llama4 text MoE self.init. Right, there we go. All right, so there's going to be a couple things that we need to keep in mind. The first one is when we look at our mixture of experts, let's pull that picture up again. A question you have to ask is how many experts? Oh, let's bring you over here. How many experts? So this router can pass a token to just one of the experts, or to two of them, or to five of them, however many you want, right? However many, and ideally it'd be, you'd want to push for sparsity, so you'd want to pick as small as you want. In the default config that I saw for Llama 4, it was set to 1. So we're basically just doing pass each token to their best or their selected expert. But we'll implement it just like they did, which will include all possibilities. So it could also be 2 experts, however many. So our data is basically how data always looks. So we're going to do rand, let's do if name equals main. And basically our verification that something is happening in this model is going to be through these kind of dummy test cases, because again, there's nothing I can do to inference something this large. We're going to do x is equal to, or actually it's called rand is equal to torch.rand. And let's do a batch size of 4. Let's do a sequence length of, let's keep it short. Sequence length of 8. And let's do a batch size of 2. And let's do an embedding dim of 32 for now. All right, let's just do that, and that should be helpful. This means we also have our config is going to be our Llama4 text config, and I'm just going to set the hidden size to, actually let's just keep it default. So typically in transformers, we'll have a 768 embedding dim for kind of, the transformers that we work with that we can actually train. So let's do a hidden size of 768. Our intermediate size of, let's do 768 times 2, and then intermediate size MLP 7. Let's also just keep it the same, right? So this will be a significantly smaller model than what we would have done with these giant weight matrices. So we're just going for learning here. So let's go ahead and write our kind of different things. So first of all, we need self.topk. So how many experts do we want per token? And we have that in our config. We're going to do config.num experts per token, right? That's going to be right here, right? How many experts do we want per token? And by default, they used 1 in the thing, so we're going with 1. We have our hidden dim. Self.hidden dim is going to be config.hidden size. We have our self.num experts is going to be config.num local experts. Okay. And now that we have that, we need to actually define our experts. So these experts and mixture of experts is no different than just a regular linear layer. It's just a linear layer, but there's just a bunch of them. So instead of just having one of those MLP modules, we'll have a bunch of them. Now, in the way that Llama does their linear layers, all of the linear layers, both in the experts and in the shared expert, which we'll look at later, they all use the standard gated linear layer method. So we'll see exactly what that looks like in just a second. So let's go ahead and write our experts. We're going to do class Llama4 text experts, right? And init.module. And so we're going to do our init self config. And we can do super Llama4 text experts self.init. Good. So let's go ahead and define all the things we need for these experts. So first, it's going to be self.num experts. It's going to be config.num local experts. We have self.intermediate size, right? So this is our projection size. It's going to be config.intermediate size, which we just set to 768 times 2. We have self.hidden size is going to be our config.hidden size. We have our self.expertDim is going to be config.intermediate size. There we go. I don't know why I have it twice, but that's fine. It's fine. We'll just go with it. And then we'll have these are our actual layers. So we're going to do gate up proj. And this is, again, a gated linear layer, just like the previous Llama models. And this is going to be nn.parameter, right? There's going to be some learnable parameters. And we're going to create a empty torch.empty self.num expert. So we have num experts of them. Each one's going to take in some hidden size, basically the embedding dim of our tokens. And they're going to each output 2 times self.expertDim, right? ExpertDim. And the reason they're going to be outputting 2 times is because we're going to chunk it up and then gate one of them with the other. And you'll see exactly what that looks like when we get there. Then we need to take our final expertDim and project it back down to our original hidden size, right? That's our down proj. So we're going to do self.downProj is going to be nn.parameter torch.empty. And we're going to do and torch.empty, if you don't know what it is basically just initializes everything as zeros, but it doesn't matter. Self.expertDim, and we're going to go back down to self.hidden size. There we go. So we have our up proj, we have our down proj, and we have these weights repeated for each expert. And this is basically where kind of my question starts, where we'll be doing one forward pass, and this will kind of make sense once we actually do it. So let's go ahead and do it. Also, I'm just going to go ahead. This isn't in the code, but just so everything is in 0 when we do the output so we can actually see something, let's just go ahead and just initialize these. It doesn't really matter because we're not using the model. Let's do self.down. So we're just going to go ahead and initialize them. Forward self x, or I called it hidden state, so let's keep it the same. So we're going to take our data and we're going to pass it through all of these experts. So here is one of the key ideas for how these experts are going to work. So I'm going to throw a pass in here for now. We're going to come back to this when we actually implement it. For now, let's go ahead and do self.experts is going to be equal to our, let's see, it's the Llama4 text experts that we just wrote with the config. And we will also have a router and our shared expert, which we'll come back to in a bit. So let's just keep going here. It's because for us to do this operation correctly, these hidden states need to be set up in a specific way. So we're going to set the hidden states up first, right? How we need to do it. And then we'll write the forward pass here, just so it's, kind of sequential in how things are working in this model. So we're going to do forward, self. We're going to pass in our hidden states here as well. And our data, right? So let's go ahead and do we're going to pass into our layer. Let's do MoE is Llama4 text MoE with the config, with our config. And we're going to pass into our MoE our RAND tensor, right? So we can check here, right? Print hidden states.shape. It should be exactly what we set it to, right? 2 by 8 by 768. Where are you, terminal? There you go. Oh, we're in the wrong screen. There you go. Okay, so now we can do Python model.py num experts per token. Did I just let's see, what did I call it? Num experts per token. Okay, there we go. Let's try that again. Okay, there we go. So that's our input, right? That's the data we're passing in. Now what we need to do is a couple of steps. So the first step, let's go ahead and store the shapes here. Batch size by sequence len by embed dim, right? Standard shape for our transformer input is going to be our hidden states dot shape. So the first thing we're going to do is flatten our batch and sequence length dimension. So what we have right now is a batch by sequence len by embedding dim. What we're going to do is flatten it so we have batch times sequence length by embedding dim. So this batch times L is basically the number of tokens, like total tokens in the batch. So we're just going to go ahead and flatten it. So it's going to be our hidden states is going to be our hidden states dot, we can do view or reshape -1 self dot hidden dim, right? We're just going to go ahead and flatten it, or we could have done embed dim here as well, right? It doesn't matter. But let's keep it to their code. There we go. Print hidden states dot shape, just so it's clear. Right, so we went by 2 by 8 by 768 to 60, right? We have 16 total tokens in this batch, so there we go. We have 16 tokens. What we're going to do now is, now that we've flattened it, we are going to get the expert for each token, right? So each token needs to be assigned an expert or multiple experts. So how are we going to do that? Well, we need a router linear layer that's going to predict for each of these tokens what are the experts that we should get. So we can define that. We can do self.router is going to be our nn.linear. It's going to be config.hidden size, config.num local experts, right? So we want for every single token, we want to predict, input, the input embedding dim for each token is hidden size, and we want to predict our output to the number of experts, right? How many experts we want. And by default, this is set to bias as false, so we don't have a bias layer here. So what we can do then is our router logits, right, is going to be self.router, and it's going to be, we're going to pass in our hidden state. So if we look at our hidden states.shape, and then we look at the router logits.shape, you will see that we had 16 by 768, so every token in our batch is represented by a vector of length 768, and now every token is mapped to the 16 different possible router layers, right? Our experts, 16 possible experts, and the router has done that. Now that we have this, we need to select the top K. How many experts do we want to send every token to? We have to send it. We have to basically index out those top K things. And this is where it gets a little bit tricky. So let's first start with our step 1, right? So I wrote this out so it's clear. Step 1, we need to pretend each expert will get all tokens. And this is the step that again, confuses me a little bit about the Huggingface implementation, because the entire point of a mixture of experts is each token should only go to the experts that it was assigned. But the way that they implemented it is all tokens will go to all experts, and we just accumulate the output at the end. And so let's just do it how they did it, and hopefully it'll be clear what's going on. So first of all, tokens per expert. How many tokens do we have? It's basically our batch, so it's going to be our batch size times our sequence length. In our case, right, it's going to be 8 because we have batch size of 2, and each batch has 8 tokens in it. So there we go. That's step 1. Step 2 is we need to get the top K experts for each of those tokens, right? So step 2, get the top K experts for each token. That should be pretty easy. We can use the PyTorch top K function, right? So we can do router top value and router indices. Router indices is going to be torch.topk, right? Top K. And we want to do it on the router logits, right? So we want the top K router logits. We're going to ask for the self.topk. So how many do we want? And what dimension do we want to do it along? We want to do it dim -1, right? We want to do it along the rows because we have number of tokens as our rows. And then our columns is the number of experts. So we want to do it along the row, right? Along each row. So along this dimension here, right? For the 16 different experts that we can get. So we end up getting router top value and print router indices. And you end up with something like this. So in this case, it's top 1, right? Because we picked 1. So these were the logits, right? The logits of the top, whichever expert had the largest logit. And these are the indexes of the experts. So this means the first token, right? So the first token in our set of 16 tokens, which was just our, our batch times the sequence length, was assigned to expert number 9. And then the second was assigned to expert number 0, expert number 15, ... right? So which expert were you assigned to? If we had multiple experts, which we could have, let's say, let's change this to 2 for now. Then we'll end up with something like this. These are the logits of the top 2 experts. And these were the 2 experts that each token was assigned to. So let's do it with 2 experts right now because I think it'll make it a little bit clearer exactly what's going on. But we'll switch it back to 1 expert when we actually wrap this part up. So now that we have that, we need to do a step 3. Create a matrix of infinities. So, or negative infinities in this case. So like I mentioned, our final goal, at least in the way that Huggingface implemented it, is we're going to take all of our tokens and pass them through all of the different experts at the same time. It's a little weird, but that's what we're going to be doing. So let's go ahead and do that. What we're going to be doing is our router scores. Actually, no, not that yet. We're going to do, yes, actually, yes. So we're going to call this router scores. It's going to be torch.full-like. It's going to be in the shape of the router logits. And we're going to fill it with negative infinities. So if we print our router scores, you should see that we basically have a big negative infinity matrix, right? In the same shape as the router logits. And that's the key idea. And now what so we can check the shape of this as well, just so it's doubly clear exactly what's going on. We have 16 by 16. Let's change the numbers a little bit. Let's make this, let's make it 10 instead. So we have slightly different numbers. So we have 20 tokens, each with 16 possible experts. Now that we have that, we need to go ahead and fill this matrix at the indexes of the top K experts selected by the router for each token, right? So that's the key idea. We want to basically fill this matrix in with the indexes of the different top K experts. So how do we do that? There is a couple ways you can do this, but the easiest way is to use scatter, right? To use the scatter. So PyTorch scatter, just so it's clear, PyTorch scatter is basically just a fancy indexing and copying operation. I think it's always a little bit confusing. The best way to learn scatter is just by doing it. But you can take a look at some of these examples here. You literally are copying from torch.0, so it's initialized as zeros, and then you're copying this data at these indexes 0, 1, 2, 3, or 0, 1, 2, 0. You're copying that data from source into here at those corresponding indexes. So let's go ahead and do that. And hopefully it'll make more sense by just looking at the results rather than just kind of explaining it that way. So what we're going to do is print out the router scores. Let's actually make the sequence length smaller so it's extra clear about what's going on. So we have, let's make this bigger. Oh, Let's make you a little bit bigger. There we go. So these are my things. So we have our 16 experts and we have the number of tokens. So we've gone ahead and created our data in our negative infinities in that shape. And now what we're going to do is copy in our router's top values. So basically, whichever one of, for this specific token, right? Let's say for this first token, whichever one of these experts was selected as top K, those experts, we're going to fill them in with the router logits. And so we can do that like this, dot scatter. And for scatter, we need to do dim equals 1, right? Because we want to do it, or minus 1, because we want to do it along each row. So it needs to know the index of the row that you're, it needs to know the which index you're indexing. It's kind of weird, but that's the idea. Index is the router indices, right? So the router indices tells me the index of along this 0th one that token 2 or expert 2 was selected, or maybe expert 2 and expert something else was selected. So it gives me the index of which things were selected. And we're going to be grabbing this data specifically from router top value. So again, this is just easiest to see through the results. It's exactly the same thing as before, but now we've copied, and let's go ahead and print out the other things. So we can do our router top value and print router indices. All right, let's go ahead and do that. So we can see that our 7 and 6 were selected as the two top experts for this specific token. And 7 and 6 had logits 1.04 and 0.99. So let's check. So it's 0, 1, 2, 3, 4, 5, 6. Okay, so expert 6 had a logit of 0.99. There you go, 0.99. And expert 7 had a logit of 1.042. There you go, 1.042. Everything else is negative infinity because they were not selected as one of the top K indices. In the same way, if we only had one expert, like we will later, right, then we'll only fill in one of those values. So we can see expert 5 was selected with a logit of 0.67. So 0, 1, 2, 3, 4, 5. So there you go, 0.67. And then expert, again, 5 was selected. And the next one, 0, 1, 2, 3, 4, 5. Dot, 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 right? So all we're doing is we have this matrix of negative infinities, and we're just filling in for the corresponding index of our expert that was selected by the router. We're going to fill it in with our logit. And the reason we're doing this is so, and let's put this back to 2 for now so it's clear. The reason we're doing this is so we can easily create some router scores. And how we do that is right now we just have a big infinity, basically a big matrix of negative infinities, and it's also full of these raw logit outputs. Now, typically we don't like raw logits. We like numbers that are between 0 and 1. So we're going to obviously apply some type of a sigmoid or softmax. And in this implementation, and for Llama 4, they use a sigmoid. So we're going to do that. Before we do that, though, we're going to do a transpose 1 or 0, 1. Right, we're going to go ahead and make it so that our number of experts dimension is first, and the number of tokens is second. And you'll see why we do that in a little bit. But this will go ahead and create something like this. So I think it's easiest just to show it this way. So basically our data now is however many experts we have is how many rows we have. And each row has number of tokens of tokens in them, right? And this is again flattened on the batch dimension, right? Batch and the sequence length dimension. So now that we have that, let's go ahead and do the rest of the work for our setup. So first of all, we need to go ahead and repeat the number of rows for the number of experts we have. So we want to produce this matrix, right? What we have right now is if we print router indices, right? We just have, transpose, there we go. What we have is this, right? And let's go ahead and just repeat it for each of our, okay, let's go ahead and do it. So what we're gonna do is we're gonna create router indices is going to be equal to, so we're getting rid of this router indices, we're replacing the variable with a new thing, and it's gonna be torch.arange, and it's gonna be tokens per expert, right? So we're gonna do however many tokens we have, num tokens here, is our original tokens per expert that we created right here. So tokens per expert. And after that, we're just going to make sure it's on the, granted, this doesn't matter for us because we are not putting anything on the GPU, but that's fine. So we're going to make sure it's on the right GPU. And we get router indices. So we should start to see some of this matrix come together, right? So we have a 0 to num tokens. Okay, we have a 0 to 8. But we need to repeat this number of experts times. So let's add an extra dimension at the beginning and then just repeat it 16 times, so, or however many we have. So we can do dot unsqueeze 0, and then we can do dot expand router scores dot, I don't know, it doesn't matter, size 0. We could have also just used self dot num experts, right? That's all the same. And we don't need to touch the other dimension, so we can just do -1. And so we get exactly what I had just mentioned. We get this, right? So we have 16 experts, so 16 rows, and each expert is for 8 different tokens in this case, because we have a batch size of 2. Each sample has 4 tokens in it. So there we go. That's our setup. Now that we have that, we will use this matrix to actually index something. So now we're on step 5, right? Step 5 is what we're going to do is we are going to grab the embeddings from the actual embed. Remember, we actually haven't done anything with the hidden states yet. We're going to grab these embeddings and store them inside our matrix using these indexes. So how do we do that? First, we can do, so let's see, when we grab our embeddings, we can do our, so let's do step 5, grab embeddings with these indexes, but we have an embed dimension as well. So if we look really quick, we have print router indices.shape, and we have print our hidden states.shape. And we actually cannot just directly, I mean, we could, but just to be as careful as possible, we have here 16, we have 16 experts, and we have 8 tokens per expert. And our original data is those 8 tokens represented by 768 embedding dim. So for me to copy these 8 tokens into these, into each one of these experts, right? Into each of these experts, I need to have an additional dimension here for the embedding dimension, right? So we just need to have that. So we'll have a 16 by 8 by 768. So let's see what that looks like. We can do our router indices. It's going to be our router indices dot reshape. We're going to do -1, 1. And we'll then do expand -1 self dot hidden dim. And this will give us exactly what we want. So this will now give us, oh, exit. Whoa, okay, sorry. Okay, so we'll end up with this, right? Something like this. And more importantly, let's look at the shape. We'll end up with exactly what we had, but now we have 128 things by 768. So exactly what is this? What happened? We have 128 things because we had 16 experts with 8 tokens each. And so what we've done is repeated them. So maybe the easiest way to explain this is by a quick drawing. We initially have basically our number of experts, right? Num experts by our sequence len, right? Sequence len, let's just call it L. Right, L. And each of these were basically one of these, right? So it'd be a vector of 0, a vector of 1, vector of 2, dot, 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 right? That's how it was. And now all we've done is just copy this over. So first of all, we flattened this dimension, right? We flattened this dimension. So instead of, actually, it wasn't like this. It was like, let's go ahead and print it out real quick. I know it's a little confusing because there's a lot of indexing going on, but it's easiest to understand if we just print out some of these shapes, or let's print out the router indices first. Let's comment you out real quick. All right, yeah, good. So let's look at that real quick. So we have here, this was our original data, right? Our original indexes. So we're gonna go ahead and just take this and fix it. So again, we have a number of experts, which was 16 in our case, right? 16. And then we have number of tokens, right? Flattened tokens. And this was 8 in our case. So we had 0, 1, 2, dot, 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 0, 1, 2, dot, 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 right? All the way up to 7 for each one of them. And so what we did is go ahead and just flatten this, right? This is basically, we can go ahead and flatten this, and we can produce something like this, right? So let's go ahead and just do it step by step. Let's first do a reshape. So we're going to do router indices.reshape. And let's print out the router indices. So we end up with something like this. 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3. So all we've done is take this thing here and literally flatten it into a big like 0, 1, 2, 3, dot, 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 7, 0, 1, 2, 3, dot, 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 right? For each of the experts. So now this is a number of experts times our number of tokens, right? Number of experts by number of tokens. And so that's what we ended up with. And what we're going to do now is just expand this out so we have our embedding dimension as well, right? Because this is still not the right shape that we want. If we look at our router indices.shape and we print our, let's see, hidden states.shape, what you can see is we have 128 token expert combinations, right? When we flattened it by 1. But we need to repeat this dimension for the 768, because what we're going to do now is take our data, which is a 8 by embedding dim thing, right? We're going to take this and expand it out. So it'll look like this. We have, again, num expert times num token. And this is going to be our embedding dim. And this entire row here will be 0, right? We're just taking the 0 here and just repeating it, taking this 1 here, repeating it. This entire row here will be 1. This entire row here will be 2, dot, dot, dot. So what we want to do then is copy, let's call this the first embedding matrix, the second embedding matrix, the third embedding matrix, dot, dot, dot. And then it'll be up to E7, right? For the 8 possibilities. So what we want to do is copy it. We want to copy at index 0, we're going to copy in our expert 0. And then we're going to, or no, sorry, not expert 0, embedding 0. We want to copy in embedding 0 because it's the 0th index. And then we're going to copy in 0, 1, 2, right? So then we're going to copy in E1. Then we're going to copy in E2, right? We're just going to copy this. We're literally just going to copy this embedding matrix in. And we're going to repeat this all the way until we get to E7. And this, right, would be the inputs to one expert, right? This is basically just one expert. And then we're going to repeat again. We're going to do again E0, E1, E2, dot, dot, dot. And we're just going to repeat this over and over again for each expert. So what you can imagine is we have these expert blocks, right? So we have these blocks that go to each expert, dot, dot, dot. And so again, this will make sense in a bit. We're literally copying it right now. We still haven't dealt with the top K stuff yet. So we'll get back to that, but let's go ahead and do that first. So we have that. We need to go ahead and do dot repeat, right, on the embedding dimension. So we have that. So we're going to do dot repeat, or sorry, not dot repeat, expand. And we're going to do -1, leave everything else the same, and self dot hidden dim. So print router indices dot shape. And you'll see now we have that, right? So we've done that. And all we're going to do now is copy it in. So before we do the copy, let's go ahead and do our step 6, right? Step 6. We need to scale our router weights. We want them to be between 0 and 1. And so this is the key step. We're going to do router in is equal to torch.sigmoid router scores. We're going to make sure it's a floating point in case there's a precision thing. But again, we don't really care about little things like that right now. And we want to make sure it's sent back to the hidden states.dtype. I'm sure there's a precision thing. So now we can look at our router in. And let's look at our original print router scores. And exactly what you think happened just happened, right? We had a -infinity matrix that was filled in for the indexes where there was a router selected. And now all we've done is convert them to anything that was -infinity gets turned into 0. And anything that isn't minus infinity just gets sigmoided, right? So what we have now is a 0 and value matrix, just like that, right? So we have, so we end up with zeros everywhere. We have values here, and we're going to use this to scale our data. So in the end, for experts that were not selected to be top K, I'm not sure why this is all 0, to be honest. Okay, I guess it was just a fluke. For experts that were selected, or not selected, for a specific token, right? For experts that were not selected, we end up with a 0 that we can multiply by. And for experts that were selected for a token, we can multiply it by its constant. So let's go ahead and do that. I wonder if it's a rounding thing. It could be I am using the wrong precision type. I don't know. Sometimes we have a whole row of 0, but that shouldn't happen. But it's fine. We will just keep going. I'm sure there's just a precision thing that I am not. dtype is equal to torch.float 32. Okay, I'm sure I'm just losing precision somewhere, or it's just rounding. I'm not entirely sure. Either way, so we have here, we're just going to scale our router weights. So all we've done is create a 0 logit vector, and if we have multiple, right? So if we go back to 2 of them, we are doing 2. Let's just go to 1 of them for now. So if we just had 1 of them, like we will when we implement it, it'll be exactly that, right? We have, here is our logit. So we sigmoid it becomes 0.81, but everything that was negative infinity are the experts that were not selected for this token, which means they all have a weight of 0, right? And so we're going to do it that way. So now that we have that, we're going to go ahead and do exactly this. So we're going to do a router in. Let's actually put that back how it was. Just, that's fine. I'll just fix it right here. Dot to hidden states dot dtype, whatever. So we've scaled our router weights. There's 0 for the non-expert tokens, or for the non-expert indexes, and they're whatever the sigmoid of the logit was on the expert one, so we can scale them. And so what we're going to do now is our step 7, gather our hidden states by our router indices, right? So we're going to gather them all up. And so again, we can just use our gather for this. We're going to route it in. And this is actually not router in. This should be router scores, right? So there you go. Router in is going to be our torch dot gather. All right, we're going to gather up. Our input is equal to dims, it should be hidden state. Our dim is 0 because the reason it's 0 is because these indexes here, 0, 1, 2, or whatever, 0, 1, 2, along each of these things, refers to the first dimension, right? The 0, 1, 2, dot, 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 right? So because these refer to that dimension, that's why the dim is equal to 0. Now that we have that, we can also do our index is then our router indices, right? That will give us exactly where everything is. That's what we set up, right? That's what this matrix is, our router indices. So we can now go ahead and print router in, and you'll see that basically we end up with this. Now let's go ahead and print out the first 8. Let's do 10 rows. Right, let's do the print of 10 rows. Does it not want to print? Let's do 4 row for R in router in. Let's print R. Let's just let it print for all of them. We don't care. That's fine. That's also not helpful. Let's just print maybe the first 5 values of R. So it's, there we go. Okay, so we have, these are just the first 5 values of the embedding matrix, but it doesn't make a difference, right? So this is the 0th token, 1st token, 2nd token, 3rd token, 4th token, 5th token, 6th token, 7th token. And this chunk here is all of my right? I have 8 tokens. I have a batch size of 2 and 4 tokens in every batch. So that's my first 8 tokens. And then notice I just start over. I started with negative 0.279. Here we go. Minus negative 0.79. Minus negative 2.79. Dot, dot, dot. So we're literally copying this matrix, right? Our embedding matrix however many times we have our experts. And there's a bunch of ways we could have done this, but this is the way that they did it, right? So we could have also just like for looped and copied it, but I'm sure the gather operation is more efficient than like writing a for loop to do this. So there we go. We have our data now just copied for every expert. But the key idea that I want you to keep in mind here is that not every token should go to every expert, right? Some tokens, a token should only go to the experts that it was selected to go to based on our router scores, right? Based on our router scores, or whichever the router decided. So let's go ahead and get rid of the mismatches. We want to zero out all of the tokens that are inside a block for an expert that it was not assigned to. And we can do that pretty easily because we have our router scores right here, right? So let's comment you out for now. Print, right? We can print our router scores. Right, again, remember, our router scores is just a zero matrix for all of the tokens it was not assigned to, and then a value, or all the experts it was not assigned to, and then a value for the expert it was assigned to, or multiple if it was assigned to. So we can go ahead and do that. Very simply, we can do our routed in. So first of all, let's do print router in dot shape. And we can print our router scores dot shape, and you'll see immediately that the shapes are close but not exact, right? So we need to flatten our router scores 16 by 8 to match the 128 because again, it's all in sequence. That's how we set it up. So if we flatten this, if we do dot reshape -1 1 and put the dot shape back, then we'll get exactly what we want. We have 128 tokens because we repeated our 8 tokens for all 16 experts, but this is just a 0, 1 or 0 logit, sigmoided logit vector, right? So we have this. So you have it looks like the first token was not selected to go to the first expert, so that's why it's 0. The second token was not selected to go to the first expert, that's why it's 0, ... And so all we need to do is multiply these things together. So we can finally do our router in is going to be equal to, let's see, routed in, let me make sure I'm using the same terminology, router in is going to be our router in times our router scores dot reshape -1 1. There we go. And so once we did that, all of the embeddings, and again, let's print it out this way, right? All of the embeddings that were assigned to a expert that it shouldn't be in are zeroed out. And all of the embeddings that are assigned to an expert that it should be in is kept. And that's the key idea, right? So we're just zeroing stuff out for those experts that they were incorrectly assigned to. And that is our final router in. And this is basically the setup that we needed to go ahead and pass it to the expert. So in the implementation, the Llama4 text experts expected the data in this shape, right? This is what I wanted. So let's go ahead and do that now. What we can do is we defined our Llama4 text experts here. So we can do, let's call this router out is going to be our self.experts. And we're going to pass in our router in, just like that. Good. So we can now check on that right here. So we can do print router out dot shape, or not router out. This is called hidden states, right? Dot shape. Okay, good. So that's our 128 repeated by our 768. So we're good to go there. So what we need to do now is multiply this by our gate up proj. So let's go ahead and do that. So our gate up proj is number of experts by hidden size, which is 768, by 2 times our expert dim, whatever that might be. And our data is number of tokens by 768. So this should work out pretty well, but we need to just do one quick shape check just to make sure it works out. Is we're going to do hidden states is going to be equal to hidden states dot reshape self dot num experts -1 self dot hidden size. So all we're doing is, if you take a look here, hidden states dot shape, all we've done is take our 128 by 768 and just put it back into number of experts by sequence len, or by num tokens by our 768. So we just took it, pulled it back apart. Again, we did it. We put it together here just so we could use the gather and stuff very easily, because gather is simple when you just have 2 dimensions. But we're just taking it back apart here just so we can actually multiply with this without any issues. Because we pulled it apart, we can now just directly do our gate up is going to be torch.bmm, and we'll talk about gate up is in just a second. It'll be our hidden states, and we're going to multiply it by self.gateUpProj print gateUp.shape. Right, so we took our data and we basically projected to a 3072 vector. So we took each of these tokens for all of the different experts. And again, this is the part that confuses me about this implementation, because technically when we do this operation here, we would want to pass each token to their corresponding expert and not just pass all of them through all the different experts. Otherwise, you kind of lose the purpose of the mixture of experts. So it's like a dense forward pass. I'm sure there's some detail that I don't know that makes this more efficient, but it's fine, right? We're just gonna go with it. So we have here our 16 by 8 by 3072. So 3072 is our 2 times our expert dim, and this is both the gate and our up proj, right? So let's go ahead and we can go ahead and chunk it, right? So this part now is very similar to the implementation of just like previous llamas, right? So they all basically use this gated method. So we're going to do gate.shape, up.shape. So all we did is take this 16 by 8 by 3072 and split it up into 2 different 16 by 8 by 1536 and 16 by 8 by 1536. And what we're going to do is pass one of them through our activation function. So our activation function is the CLU activation function is what they use. So act function is equal to nn.clu. And we'll talk about exactly why we do that in just a second, but let's finish implementing this. We're going to have our, we're going to do our gated. It's going to be up times self.activation function on our up, or gate. There we go, gate. So let's quickly take a look at CLU. If you haven't seen it before, it looks basically like ReLU, but you have a little bit more bandwidth. Here we go. So here's ReLU versus CLU. And what you can imagine is for numbers that are greater than 0, they're kind of just left alone. Numbers that are less than 0, we have a dip, but they're basically close to 0. And this is a gating mechanism, because what have we done here? What we've done is take our gate, right? We chunked our data, we took the gate, and we passed it through this activation function. So either these values are close to 0 because they're less than 0, or they're kind of left alone because they're greater than 0. And what we're doing is taking up, which is the same shape, and multiplying it by it. So up is either getting multiplied by values close to 0, which reduces their magnitude, or it's getting multiplied by values that are, not basically left alone, so that would increase their magnitude. So this gating mechanism allows for some more fine-tuned control over what kind of information can actually propagate through. And that's actually pretty neat. So this is a standard setup for the, I believe previous llamas also use this method. So it's here as well, but now it's here in all of the experts rather than just, just a single, rather than just having it in a single multi-layer perceptron. So let's take a look at our gated.shape. We have here, right? That's our output, but these values are now either, close to 0, or they've been, scaled up based on whatever the CLU activation allowed to get through. Now that we have our gated, all we need to do is take our data, right, which is currently in the self.expert dim embedding dim, and project it back down to our hidden size. So that's very simple. We can just do next states is equal to, again, torch.batch matrix multiplication gated self. We could also just use like the ampersand or the @ symbol, right, to do these matrix multiplications, but it's fine. I'm just trying to keep it like their code. So print next states dot shape. What do we end up with? We have our 16 experts. We have our 8 tokens, which again, these 8 tokens is a flattened batch by sequence length embedding dim. And we're back down to 768, right? Embedding dim for each of them. So we've returned back to where we started. Now to make this usable for later, what we need to do is next states dot view, and what we're going to do is just flatten everything, our number of experts by num tokens, by our hidden size. So -1 self dot hidden size print next states dot shape. And this is just to return it back, right? We started with that shape when we came in, right? If we print hidden states dot shape, right? We started with that shape when we came in. We did our gated linear layers, multi-layer perceptron, and it was gated for all the experts. So there we go. And then we just returned it back to that shape at the end. So there we go. That's our final output. Nothing too crazy, right? We're going to implement this one more time when we do the single one, the single multi-layer perceptron in just a bit, but it looks exactly the same. Return next states. Okay. So now that we have that, we can X out of this. Let's print our router out.shape, and you'll see that we have our output there. So we're good. Let's get rid of you. Don't need you. Good. So we have our output. And this is, again, basically this is it. This is the mixture of experts happening. So this is our mixture of experts, MoE. But if we take a look at the figure one more time, I need to stop closing this. Let me pull it back up again. We have two things going on. We have both a routed experts, mixture of experts, but we also have a shared expert, and we just add them together. This shared expert is just another feed-forward layer, right? It's just another feed-forward layer. So we're just going to do this separately and then just add a result at the very end. So let's go ahead and do that. So we need to implement one more layer. This will just be, they call it class Llama for text MLP nn.module def init self config. There we go. And so we're going to do super Llama for text MLP self.init. There we go. And this is going to look identical to what we just done. We can just store the config in here. We can do self.gateproj, right? Our gateproj is going to be nn.linear. It's going to go from config.hidden size up to config.intermediate size. Oh, intermediate size. We could have also done this with a single linear layer, right? We could have done 2 times here, but it's fine. I want to keep it the same. So if I ever do get to load weights into this and actually run it, then the weight layers are all the same. So there's no confusion. We'll have a up projection, which will exactly be the same thing. So that's this, right? I did a gate up here because I took my data and projected it to 2 times the embedding dim that I wanted. Instead of having one weight matrix to do that here, I now have 2 of them, right? So I don't have to do the chunk operation anymore, but it's all the same, right? It doesn't really make a difference. Self.downproj is going to be nn.linear config.intermediate size. So we're going to go from intermediate size, and we want to go back down to config.hidden size, just like that. And so that should be good. And by default, in all of these, the bias is set to false. Bias is false, bias is false, bias is false. There we go. And everything else is going to be the same. We still have the same activation functions. We're going to do self.activation function is nn.clu, right? Just like before. Oh, clu. And we're going to do def forward self x, and we can do our gated. This is going to be the same as before. It's going to be self.activation function on our self.gateproj x, and we're going to multiply this, right, the clued output of this projection by self.upproj x, right, same input, and then we can return self.downproj gated, right? We're going to return that back. And that's it, right? So again, these 2 things are identical. This is just doing it for a single linear layer or single multi-layer perceptron, and this is doing it for num experts numbers of multi-layer perceptrons, but it's the same thing otherwise. So now that I have that, we now can do our shared expert, right? And the shared expert is just going to take our data and output it. So nothing crazy. It's going to be our shared expert out is going to be self.shared expert, and we're going to pass in our hidden states, right? And these are just the original hidden states that we started with. We need to define it up here. Self.shared expert is going to be our Llama4 text MLP config. And there we go. So if we look at our print, our shared expert out, we should get our result, right? So, okay, so we have a expert. Now let's see, missing a forward function. Forward. There we go, right? So that's our final output. And now here is the key idea, the most important idea. What we have as the output of the shared expert is this. We have a, and let's print out the shape just so it's clear. Shape. We have number of tokens by embedding dim. And again, this num tokens is a flattened batch by number of tokens, right? Or sequence length. So what we have is a num tokens by our embed dim. This is the output of our shared, right? The shared is right at the bottom. This is our shared. Shared experts, right? Shared expert. On the other hand, from the other thing, from our mixture of experts, we have num tokens times num expert, right? We have number of tokens times num experts. We also have the embed dim here. Right, so there we go. And this basically is chunked, right? Like we have the first chunk is for the first expert. The second chunk is for the second expert. The third chunk is for the third expert, ... however many experts you have. And the other key idea is all the rows are basically 0 for the ones that are incorrectly assigned, right? So we went ahead and did that, right? We multiplied our outputs and we passed in zeros to our kind of expert projections, and we then have a bias. So if we multiplied by a bunch of zeros, these are still zeros. By the way, we have this. This is our setup. And so what we need to do now is collect all of the correct. So let's say this token. So let's say 0. Let's pick a different color. Let's say we have 4 tokens in this. So 0, 1, 2, 3, and then again 0, 1, 2, 3, 0, 1, 2, 3, ... right? So we have these repetitions, right, every single time. And let's say token 1 was assigned to this expert right here, right? So this is the correct one. Everything else was 0, right? So let's say nothing else was assigned. That means we need to grab, right? We need to grab this token 1 here and add it to the corresponding token 1 right here, because it's an add operation. But we only want to add them for all of our tokens, right? For the correct one. So we want to add this there. Let's say token 0 was assigned to this expert here. Then this token 0 should go up and add right here, right? And we want to repeat this for all of them, only for the correct ones. Now, we could, again, do a for loop, but remember that our input to our, before we passed it through the mixture of experts, the input was just a bunch of zeros, which means if this 0, if token 0 was not assigned to this specific expert, the input would have just been a bunch of zeros because we zeroed it out with those weights. Well, and if you remember, our entire operation, right, the entire mixture of experts operation was just a matrix multiplication, which is right here, right? It's just a matrix multiplication. There's no bias, which means after doing a matrix multiplication on a bunch of zeros, your output is still 0, right? Nothing changed. So if the output is 0, then we can go ahead and just add everything together, and it'll basically just accumulate in, right? So we're going to add, let's just do the first token. We're going to add, let's say 0 was assigned to this one right here. So that means we're going to add this 0 right here, which is the incorrect one. We're going to add that to the 0th token. And then we're going to add this to the 0th token. And then we're going to add this to the 0th token. It's going to repeat that over and over again for everything, right? Just repeat that over and over again. And that will accumulate things in. And it'll accumulate it in 2 ways. First of all, for tokens that were for basically the experts where that token does not belong, it's just going to add 0. So it doesn't do anything. On the other hand, remember our final output, these have been scaled for the correct ones. Let's say our token 0 is assigned to 2 different embeddings, right? Or token 0 was assigned to 2 different experts like this, because we did top k as 2. That means we're going to add And remember, this was multiplied by some sigmoid of some logit for expert, let's do expert 2. And then this was multiplied by the sigmoid of some logit of some expert 3, right? We multiplied them, and again, that was literally, that was this code, right? That was the code right here, right? Multiplying by the router scores. This was also multiplied, right? This was multiplied, but this was multiplied by 0 because it was the sigmoid of negative infinity, right? So that's why this ended up just being 0. Either way, we're basically just accumulating in exactly like that, even for this one. So it will add up everything for that first token, 0th token. It'll add it all up, and things that were 0 won't contribute, and the things that weren't 0 will contribute. And so again, there's a bunch of ways we can do this. We could write a for loop, or we could just use the scatter add operation. So you can go ahead and look in the, here, let me actually pull up these scatter add docs so you can take a quick look at it. But it's exactly like scatter. I need to stop doing that. Come back, there we go. So it's exactly like scatter. Nothing, it doesn't change from the scatter operation that we did, but instead of indexing, instead of storing the values like we did when we scattered, it's going to accumulate the values. It's going to add it all together. So you can take a look at this. Let's go ahead and do that. So it's very simple. So what we want to do is take our shared expert out, right? Our shared expert out, and we're going to do dot scatter add to avoid doing a for loop. We want to add along dim equals 0, because again, remember, the index is still along our dim equals 0 because the index is our router indices, right? Which expert did we go to? And the experts is our first dimension, as we have here, right? We have 16 times 128. That's fine. So now that we have that, we can do our index is going to be our router indices that we had from earlier, right? So let's remind ourselves again, print router indices shape. Let's comment you out. And less than the shape, right? It was this matrix, right? Repeating num experts, repeating every block of num tokens, num expert number of times. And these are basically our indexes to access the different embeddings. And the thing is that basically it's saying that this belongs to the 0th token. So it's going to add the 0th embedding, right? So yeah, the indexing always gets a little challenging, but let's go ahead and just try to be crystal clear about this, because I think this is probably the toughest part of the implementation. So we have 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, and then let's pretend the total is 4, right? Total token. So again, we'll do 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, dot, 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 right? This is our matrix. And then what we have corresponding with this, right, is our matrix from up here, right? This matrix right here, right here. So we have the actual embedding values for all of them, the output of the mixture of experts. I'm just going to call this the MoE output, right? So these are corresponding with each other. And then we have our scatter output. So that will look like this. So this will just have 4 indexes, right? 4 tokens, and we're embedding them just like this. And so what it's going to do, right, how this is going to work is it's going to say, okay, I have this thing here, which lines up with this vector right here, right? This embedding right here. And I want to add all of these things to the 0th index of this right here. So that's going to go ahead and take the 0 and add right here. And then after you work your way down, right, 0, 1, 2, 3, again, 0, 1, 2, 3, it's going to take this one here, which is all zeros, and add it to here again. It obviously will go in order, so the next one would be, oh, I want to take this one here and add it to the 1s. I want to take this one here, add it to the 2s. And then it'll repeat, right? So again, when we get to 2 again, it's going to add it again to the 2, so on and so forth. So it's just going to repeat it. That's all the scatter add operation is doing. So we can do scatter add, router indices, and we will have our source is our routed output. There we go, right? So, or sorry, not routed, router output. So it's going to take the stuff from our experts and accumulate them into our shared expert out. And now that we have that, we can return our shared expert out. And this effectively completes our mixture of experts implementation. Right, so this is the entire mixture of experts happening. It's probably the most annoying part of this whole implementation. Everything else is going to be very similar to all of the kind of previous Llama stuff, like Llama 3. Again, the caveat here is the decision that they made to basically do a full dense forward pass on all of the tokens on all of the experts is definitely interesting. I'm sure there's a reason for it. I just don't know what it is. In a more ideal implementation, maybe it would require like a CUDA kernel kind of type of implementation. You would only pass the tokens to the expert that they are actually assigned to, rather than sending them to all of them. But either way, I digress. This is just a kind of just an experiment, right, to explore a little bit about what's going on in this implementation. So we now have our text MoE. What do we want to do next? I think we should just go on to Rotary Embeddings. So let's quickly check here real quick. Print shared expert out.shape, just so we know what we're working with. Oh, good. So I have a bug. So we have router indices. Did you mean shared? Oh, expert out. Just make sure we know what we have. And there we go, right? That's what we started with. So 8 by 768 by our, right? So it's our num tokens by our embedding dim. Good. This router out, I wonder why it's, maybe VS Code's just being a little weird. That's fine. Let's just keep moving. So what we're going to do now is our rotary embeddings. And this part is challenging for a completely different reason. Llama4 text rotary embedding. nn.module. Okay. So init self config device is just none. It's fine. And what we're going to do is super Llama4 text rotary. I feel like my VS Code is being weird. Let me just close it and open it. This is why I use Vim for everything, but no one wants to watch me type on Vim when teaching. Okay, now it looks more right. Self dot init. There we go. Oh, this should be class. Sorry. Okay, good. Yeah, okay. So our rotary embeddings, let's kind of remind ourselves a little bit about what rotary embeddings are. Again, I'm assuming you have seen it before. Otherwise, this video would take forever. But yeah, please just go take a look at some of the resources I already mentioned, and it'll be helpful. But let's kind of take a quick look here. Rotary embeddings are an alternative form to the sine cosine embeddings that we've seen and the kind of the learnable positional embeddings that we've seen. And the main, the cool thing about them is what they do is we have a embedding here. So let's say for the word enhanced, we have an embedding, right? So that's what it is. And we chunk our embedding up into chunks of 2. So we take the first, so there's 768, let's say, right? A token embedding, 768. We take our 768 and split them into kind of chunks of 2 like this. And we take each 2 of them and rotate them by some constant, right? We're literally rotating them. And the implementation that I have done multiple times before looks kind of like this, right? And this is the one you'll see in most places, but it's not the one that they decide to go with. So if we take a look here, you'll see that we have models. No, I'm looking for models, components. Here we go. And we have our rotary embeddings. And this is a very familiar implementation that you'll see. Basically, you'll have your rotary embeddings. You'll create these inverse frequencies. You'll build a sine cosine cache. And then you'll have this interesting operation to do rotate half. Like you'll take 1, 2, 3, 4 and split it into like -2, 1, -4, 3, ... That's how you'll do it. And then you'll actually do x times cosine plus rotate half x times sine, and that will give you your rotary embeddings. And where does that come from? That comes from here. So they give you a nice formulation. So here's x, here's my rotate half x, right? So we have x1, x2 becomes minus x2, x1, minus x4, x3, dot, dot, dot. And we'll multiply it by cosines, the x by the cosines, and we'll add this when multiplied by our sines, right? So this is the typical formulation. In the case of the implementation here, and I guess this is how you can do it as well, it's equivalent of doing this entire operation, like all of this extra work that we have to do is actually handled in the complex space. So when you multiply a complex number to another complex number, you're actually just rotating. So a multiplication by a complex number is a rotation. So instead of doing it here, why not do it like what they have here? Just do it all in the complex space, right? So there we go. So we're going to be implementing the rotary embeddings in the complex space because that's how they do it in their implementation. It doesn't change anything. It's not too complicated, but it's just different. So that's why I wanted to mention it. Self.config equals our config. So our self.max sequence length cache, right, is going to be config.max position embeddings, right? So what's the max context length of this model? And we saw it was 4096 times 32. And then we have self.original max sequence length. It's going to be config.max position embeddings. They're both the same. I'm not really sure why I have both of, or why they had both of them in their implementation, but fine. I'm trying to keep it as similar as possible. So step one is we need to compute the inverse frequencies, right? So if we go back to our rope paper, right, we need to compute these inverse frequencies. That's basically these thetas, right? We need to compute these inverse frequencies, and then we'll scale theta by m, right? A constant of what position are you currently in. So let's go ahead and generate our inverse frequencies. There is a formula that I don't remember exactly where it was. Oh, here we go. Right, this is the formula. So they use 10,000 here as their base for their frequencies. In this paper, in Llama, they use 500,000 because the context length is much larger. So they want a much more gradual decay, basically. So there we go. So let's go ahead and do that. We're going to do inverse frequency. Inverse frequency is going to be self.compute default rope parameters. And another discrepancy between what I'm doing here and what is probably being used in the actual like Llama4 models is they're probably using a scaled version of rope, mainly because like you can then change the context length, but I don't want to go into kind of details like that. It has no purpose for actually learning what's going on, and this should be fine. I think that scaling only kicks in when you exceed the context length, and the context length is already ridiculously big, so it's probably fine. So compute default rope parameters, and it's very simple. We're going to pass in ourself, we'll pass in our config, device, whatever. Okay, so our base is going to be our config.rope data, right? It's what it's called. Rope data is our base. And then our head dim, and I believe it's rope data. Let's double check. Rope data, yeah, rope data, right? That's our base. And now that we have our rope data, our head dim, right? The rope embeddings, again, if you remember, are applied to the queries and keys, right? But it's applied on each head independently. So it's on the head dim. So we just need to get that. Our head dim is just going to be our, let's see, config dot head dim, just like that. And so our inverse frequencies, right, is then, let's just follow the formula. So it was, we can do one, it's to the power negative. So we can just do 1 over, right? So we can do 1 over, and we'll do base to the power, and it's going to skip every other one, right? It's 2 times ID. So let's go ahead and do that. It's going to do torch.arange. Right? We're going to go from 0 to our head dim in chunks of 2. Because we want, remember, in chunks of 2, we're going to grab the first 2 embeddings of the head dim, the second 2 embeddings of the head dim, dot, dot, dot. Right? So we're going to grab them in chunks of 2. So we're going to go from 0 to head dim. And we're going to make sure that this is on the correct device, dot to device equals device. In case you're doing this on a GPU, and D type is torch.float. We're going to make sure it's floating point. So that'll go ahead and do that. And then we just need to divide by the head dim, right, to scale it. head dim. And so we can print our inverse frequency, and we'll see that model.py. Let's see. Oh, I actually need to run this. So let's do, let's leave yall for now. Let's do rope is our rotary embedding. And I think that's good. That'll hit the init. So it looks like we have a bug. I probably spelled something wrong. Compute default rope parameters. And there we go. Those are our very small rope embeddings. Which am I missing? I have 1 over base to the power torch.float. Oh, my bad. I need to divide by the head dim in here. Divide by head dim. There we go. It has to be inside. On this, yeah. Good. Let's double check again because we have over d, right? Over d in the exponent. So it needs to be actually inside the exponent, and then everything else is fine. So now we should get rope embeddings. There we go. So these are our initial data, right? That's our initial data. And what we're going to do a little bit later is take this data and multiply it by m, which is just our position of which token are we currently at, right? So m is 1, m is 2, m is 3, dot, dot, dot. So we're just going to scale this up. So we'll see that a little bit later. But for now, let's just keep going. We're going to return our inverse frequency here. And so we can now do self.register buffer, right? Because this isn't a trainable thing, it's just a constant. So we can just go ahead and store it in a buffer. Inverse frequency, and we can do persistent is false. So if you were training a model and saved it, then this buffer would not be saved inside our weight matrix, right? The saved weights. So there we go. And of course, there's nothing learnable here. So we can do at torch.noGrad. It's nothing learnable. And we can do def forward self x. And we're going to pass in something known as position IDs. And the position IDs are basically just an identifier of what position are we currently at for every single token, like 0, 1, 2, 3, whatever it may be. So let's just go ahead and create some dummy data for that and give it a try. So we have our rand. Let's do our position IDs is going to be torch.tensor. In this case, we have 0 through 4, so we're going to do 0, 1, 2, 3. D type is torch.float 30. Actually, we can do int, right? These are just integers. And then we can do print position IDs. We need to repeat this for all of the samples in the batch. So I need to throw a pass in here. So we need to repeat this up. So we have 0, 1, 2, 3, but that's only for the first sample, right? We have multiple samples. So we can do dot unsqueeze 0 and then dot expand to -1. And I believe that'll work. So there we go. So we've just repeated these position IDs, telling me where I am at every step. So there we go. So with these position IDs, very simple, we will do inverse frequency expanded, right? So currently, right, our inverse frequency is it's basically just a vector, right? It's a vector of length, our head dim divided by 2, and that's it. So what we want to do is add dimensions and repeat for the batch size, right? Just so we have the batch dimension. So what we're going to do is our inverse, let's do self.inverse frequency. And we're going to give it a batch dimension. So we're going to throw none at the beginning. And we're going to give it another dimension at the end. So what we'll end up with is a batch by, I'll just say head over 2 by 1. That's the final shape that we've created here. And now that we've done that, we actually need to repeat it for the batch dimension. So we need to expand. And we can do our whatever position IDs dot shape 0, it doesn't matter, and then -1 and 1. So we're gonna leave the middle one alone and then just repeat the last one time, which is just do nothing with it. To x.device, so just make sure it's on the right device. So now we should get our inverse frequency expanded, just repeated, right? Inverse frequency expanded. Oh, I have to actually do the forward. So let's do rope, and we're going to pass in our rand and our position IDs. And we can get rid of this print statement. There we go. And looks like we have another problem. Inverse inverse, INV. Okay, so that's right. We've just taken our inverse frequency here. We have it once, and then we have it twice. We just repeated it twice, that's all. So nothing crazy. Now that we have that, we can now take our position IDs, and what we want to do is basically scale it. So remember, we want to take these inverse frequencies, right? All these inverse frequencies that we have here, theta 1, theta 2, whatever, which is what we have right now. We have all of these thetas, and we've just repeated these thetas for the batch. But we want to multiply them by 1, 2, 3, 4, dot, 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 for all the different positions, effectively scaling it. So what we have right now is, let's just keep track of the shape. This is going to be a batch by our head over 2 by 1. Let's make these little x's. That's what we have. And our position IDs, right, which tells us what's the scaling factor, like how much are we multiplying by? What is the position at this specific token? So our position IDs is going to be, again, it's a batch by L, right? Batch by L. So for me to multiply these things together, I need to go ahead and add another dimension to my data here, to my positions, to do it batch by L, or batch by 1 by L. And if I multiply this by this, it will effectively just go ahead and repeat this operation. So, okay, so it'll make sense in just a second, but let's just go ahead and do it first. So it's getting a little bit ahead of myself. We're going to do position IDs is our, and we're going to call this position IDs expanded. Is going to be our position IDs. And we're just going to add a extra. You could have also done this with unsqueeze. We're going to add an extra dimension here. Just make sure it's a floating point. Position IDs. And so now we have our position IDs, right? We just added an extra dimension, as you can see. Or sorry, position IDs expanded is what we want to take a look at. There we go. We've added an extra dimension. Nothing crazy. And now that we've done that, we get the benefit of, if we multiply a batch by head over 2 by 1 by a batch by 1 by L, then it'll basically just accumulate, right? These are just one numbers anyway. So this is going to do that operation of multiply each one of these thetas by each one of these indexes, right? That's the operation. We're just going to multiply each of these by each of these indexes. And so it's literally going to create a batch by head over 2 by L, right? Simple matrix multiplication. They do this under a autocast flag. So we're going to do width.torch.autocast. I'm sure there's a reason for this. Device type is x.device.type, and then enabled equals false. So they don't want to do this operation in mixed precision. I'm sure there's a reason for that. Maybe you'll end up losing some of the information. So we're not doing it in mixed precision. We're just doing it this way. So we're going to do frequencies. It's going to be our inverse freaks expanded. And like I mentioned, we're just going to matrix multiply with our position IDs, and we'll get our frequencies. And more importantly, what am I missing? Because I need to do position IDs expanded. Right, so we get our frequency. So we can see here's the frequency of the first thing, the second token, the third token, fourth token, so on and so forth. And notice the values are always the same, right? So this one here is the second token's embedding. Well, here you go. That's the second token's embedding. So we've created our frequencies, and more specifically, if you look at the shape, if we look at the shape, we get a 2 by 64 by 4, right? So for, we end up with everything we need. Our batch size by our h over 2. So remember, our head dim was set to 128, somewhere here, 128, right? So h over 2 is 64. So we got our batch size, head over 2, by our 4, right? Our sequence length in this case, because we only have 4 words. 4 tokens. Great. So now that we have our frequencies, we can go ahead and we want to transpose it. We want it to be batch by sequence len by head over 2. So we're going to do freaks is going to be freaks.transpose, and we'll flip the last 2 dimensions, 1, 2. And then we'll do freaks sys, right? So these will be our final frequencies. And this is the key part. We're going to convert our data to polar coordinates. So what we're going to do is torch.polar. It's going to convert to polar. We want to make sure that when we convert our data to polar, there's two things you need, right? You need the magnitude and the angle. We have the angle, that's the frequency. What we don't have is the magnitude. Now we don't want our rotary embeddings, right? When we do this operation here of rotating a vector, we don't want it to scale the vector. We want the vector's length to stay the same. We just want it to rotate, right? Rotate around the axis. And to do that, all we need to do is make sure that our magnitude is always 1. And we can do that. We can say our ABS, which is the magnitude, is torch.ones like. And it's going to be our frequencies. So there we go. And then our angle is going to be our frequencies. So this will create a freaks sys.shape. So we can see first, everything's the same. We just flip the 2 dimensions. But more importantly, we have converted all of our numbers to complex numbers. So they're 1 plus j theta, right? So we have our complex numbers now. Nothing really changes. It's just a different representation. So we're doing it in the complex space, so we can turn that entire operation of doing the flipping and multiplying by sine and cosine and adding it all together. All of that gets dealt with by itself in the complex space. So we can do it there. So let's do our return freaks sys. So these are basically the frequencies that we want to apply to something, right? Apply to something. All right, let's now go ahead and apply these rotary embeddings to data, right? So let's go ahead and write a function for this. It's going to be apply rotary embedding, right? There we go. And it's going to take in our Q, our K, and our frequencies, right? Freaks, there you go. Then take in those frequencies. So one first thing is that when we actually do this, our data won't look like this. It's going to be in batch by heads, by sequence length, by head dim. Right? So let's just go ahead and write it like that. Let's just kind of pretend that we're doing it something like this. Right? So I'm just taking our data, cutting it up like that. And let's go ahead and now set up the rest. So step 1 is let's kind of remind ourselves, we want to take every consecutive pair here and rotate them individually. And rotate them by how much? We computed the frequencies, right? That's our m theta 1. And we basically want to take this x1, x2 and rotate by m theta 1. Now the thing is that when we want to do that, we can't do operations between just x1, x2, our data, and complex numbers that we set this up. So we have to convert this to a complex number as well. And we'll get that to a bit. For now, let's go ahead and chunk our embedding dim up into chunks of 2. And that should be pretty easy. We can do xq is equal to xq.float. Just put in floating point, and we're going to do reshape xq dot shape everything but the last dimension, and then the last dimension we're going to split into -1 and 2. So we'll get xq dot shape, and basically this 64 head dim should get split up. Into I guess I have to actually apply the function apply rotary embedding between xq. Or actually, in this case, let's just pretend xq and xk are both these rand, so rand, and then freaks sys, just like that. And so we should get something. So we've taken that last dimension of 64, the head dim, and cut it up into chunks of 2. So this is this operation, me taking this and chunking it up into chunks of 2. And this happens along every head dimension, right? Because there's multiple heads of attention, so it happens on each head dimension individually. So we have our chunks of 2. And now we're going to obviously repeat this for queries and keys, because they're the same thing. xk is xk. xk, there we go. So that chunks it up. And now, like I mentioned, the only way to do this, because our frequencies are in complex form, we need to make sure these are complex as well. So how do we convert this to complex? First of all, if we take a complex number of x1 plus ix2, right? So x1 plus ix2, and then multiply it by the complex number representing this, that's the rotation, right? That's the rotation. And so all we need to do is just represent it like that. What we have right now, and I think it's best just to see it through the picture, what we have right now is every single token has been chunked into basically this, right? So the first embedding 0, 1, 2, 3, 4, 5, 6, 7. So we've taken each of the our full embedding length of 64, the head dim, and chunked them up into chunks of 2, just like this. And what we want to do is rotate each of these two-dimensional vectors by their corresponding theta, right? Determined by the frequencies. So to do that, all we need to do is convert E0, E1 to E0 plus J E1, E2, E3 to E2 plus J E3, right? So convert this to complex form. And this is actually pretty easy to do. They have XQ, we'll call it XQ splits again. And this should be XQ split as well. XK split, just so it's different. So we have our XQ split, and what we're going to do is very simply torch.view as complex. So view as complex basically takes the last dimension, expects there to be two things there, and then converts it to a complex number. So we can take E0, E1 and just put them together to become E0 plus J E1. So if we look at our shapes real quick, print XQ split dot shape, and then also look at it afterwards, right? What just happened? We took our batch size by number of heads, by sequence length, by our embed dim divided by 2, by the embed dim, and it puts those values together, right? We go from 2 and we lose that dimension. Why does that happen? Because we can actually look at the shape. So let's look at this for maybe the 0, 0, 0. Let's just index in. So 0, 0, 0. Yeah. And then again, 0, 0, 0. We're looking at it for one token. So we can see this is one of the embeddings, right? If we flatten this whole thing, that would be one embedding. But we chunked it up into chunks of 2, just like we wanted. And so the first chunk is 0.65 minus 0.23. Well, here you go, 0.65 j times minus 0.23. So we've taken these two numbers here and just turned them into the cosine and sine of your complex number. So there you go, that's our complex number. And so all we've done is convert our q's to a complex number. And similarly, we'll do the same thing to our case. So we're going to do that our XQ split, and now we can do our XK split. So now we have converted our things to complex numbers, and all we need to do now is take this complex number, x1 plus jx2, multiply it by the complex number of m times theta 1, which is our frequencies that we computed already, and that is effectively the rotation, just in the complex space. Again, we could have done this. Doing this operation would have been identical, but it's fine, right? It's not a big deal because we're not computing gradients here, so we can just do it this way and it's fine. So now that we have that, we can do our XQ out. Let's check the shape here real quick. Print XQ split dot shape, and look at our frequencies dot shape. And you'll notice we're missing one thing. We have a batch size by number of heads, by our embed dim, right? We're basically missing a dimension, right? So we're going to add an extra dimension so we can parallelize this operation. So let's go ahead and do that. Our XQ split, let's go ahead and do this. And actually, in this rotary embedding, before we do it, this is my bad. When we do the rotary embedding, it's before we do the transpose. So actually it should be batch size by sequence length by our number of heads. There we go. So it'll look like this, and then we'll do the transpose later. But at least in this implementation, this is what the tensor will look like. It'll be batch size by sequence length by number of heads by embedding dim. So now we will have a let's print those again. Print XQ split dot shape, XK or X. Let's see. Freaks dot shape, the frequencies that we want to compare to. So we're missing a dimension. We have a batch by sequence length by heads by head dim, and we need an extra 1 in here as a dummy dimension for the number of heads. So let's go ahead and add that in and multiply, right? So it's going to be very simply XQ out is going to be XQ split, right? That's our split up embeddings, and we're just going to directly multiply it by our frequencies. And we're just going to add that extra dimension in right there. And this whole operation does that rotation exactly the same way, because multiplying complex numbers is the same as rotating them. And we're again going to do exactly the same thing for XK out. It's going to be XK split, same frequencies, but there we go. So that goes ahead and does that. And if we look at our XQ out, what we have is the final, looks like we're missing a shape still. 32 must match let's check here. Head dim. So we need to make sure our head dim's the same because we have it as 128 in this model, right? Up here, head dim's 128. So let's just half it. So if we have 768 and our head dim is 128, that means this one should be 6, right? 6 times 128 is 768. Now let's see if this works. Nice. Okay, there you go. Yeah, so it's just a shape thing. We have to make sure it's all the same. We can actually make this. Let's make head dim equals, or no, head dim equals 64. Right, let's just do that. So that'll make it equivalent to kind of what we're used to with our shapes. So there you go. Will this still work? Yep. Okay, good. So if we look at the output shape, right, that's our final output. Let's get rid of U. Put that space back. There we go. So that's our final output. Let's run it one more time so it's easy. So we have batch size by sequence length by num heads by our embed dim. But these embed dims are complex, right? And they've already been rotated, right? So they're the complex final value of our rotated embeddings, pairs of embeddings. So all we need to do is take these complex numbers and convert them back to real numbers. So very simply, we can do xq out. And so what that means is it's going to take a plus j or I times b, right? Complex number, and it'll convert it into a tensor of just a, b, right? So it's going to split them back up, and we'll get that 2 dimension back, right? We lost it when we converted to complex. We'll get it back when we convert back to real. So let's go and do that. That's going to be xq out is equal to torch dot view as real, and it's going to be xq out. And similarly, xk out is going to be torch dot view as real xk out, just like that. So that goes ahead and gives us our final outputs of print xq out dot shape. Right, so we get our batch size by sequence length, by number of heads, by embed dim, by the 2 that we chunked by. So now we can put the 2 and 32 back together. So let's go ahead and flatten it. We can do dot flatten after the 3rd dimension, right? So everything afterwards. Flatten 3. So that'll go ahead and 0, 1, 2, or 0, 1, 2. So it'll flatten these last ones, 3 and 4. That's going to flatten them, and that will give us back to batch by head, what we started with, right? It'll get us back to what we started with. But the rotations are now done. And so we can now return xq out dot type as, just make sure the type is the same when we return. In case you're doing mixed precision training, xq out dot type as xk. And that completes our rotary embedding. So this is the first rotary embedding. We're gonna have to do it again for the vision portion of this model, but that's the key idea, right? So we now have completed our rotary embeddings. Now it shouldn't be too bad. Now it's basically just pipelining stuff through the model, and the rest of the transformer is just a regular transformer, right? There's nothing fancy happening, so let's just go ahead and go through it. So there's 2 types of normalizations that we have that look similar but are slightly different. One's just a basic L2 norm, and the other one is the root mean squared norm, RMSNorm. So let's go ahead and do this. So we're going to do class. We won't need them just yet, but we will need them a little bit later. So that's why we're going to write them now. Class Llama4 text L2 norm and n.module. And this will be very simply init self EPS, right? So just a 1e minus 6. And all we're going to do is do the basically the root square norm, right? Yeah, okay. So we're going to do super Llama for text L2 norm self. Having a tongue twister today. I was up all night trying to figure this code out so I could give this today. So I'm a little bit tired, but that's okay. I'm totally locked in right now. We have norm x, and what we want to do is x divided by, so let me just copy this part in. We want to do this. This is the operation we want, right? We want to divide x by the square root of the mean of x squares along the last dimension, right? So we want to basically average up the square. We want to average up the square of our embeddings, take the square root and divide x by that, and that'll be our our normalization. So that's going to be return x times torch.r square root, which is just reciprocal, right? So we're going to be 1 over reciprocal square root x.pal 2, right? We're going to square it. We'll take the average along the last dimension, the embedding dimension, but we'll keep the dim, otherwise the shapes wouldn't work out. And just to ensure that we're not doing some divide by 0 stuff, we're going to add self.eps to it, right? So we're not dividing by a 0. There we go. Very simple. And so our forward is going to be self x, and we just return self.norm x. And for some reason they keep doing these typecastings. I'm sure there's something to do with mixed precision not being happy with some of these operations. So we're going to make sure it's a float and then back to x, right? Back to the same type that we started with. So that's the first one. That's just regular L2 norm. And then there's also RMSNorm, which is exactly the same thing. So we can do class Llama for text L2 norm. It's just this one, RMSNorm, also has an additional scaling factor, right, for the variances. So we're going to do def init self EPS again. Actually, first hidden size we'll pass in, and then the EPS is 1e minus 5 in this case. Okay, fine. Super Llama for text, and this shouldn't be L2 norm. This should be RMS norm self dot init, just like that. So we have everything we need. So again, everything else is the same. We have the self dot EPS is just the EPS from before, and self dot hidden size is our hidden size. And lastly, our self dot weight, right, is going to be nn dot parameter, and it's going to be torch dot, we're just going to initialize our variances, right, as 1. So there we go, hidden size. And so def forward self x pass, and then we also need to norm, right? So def norm self x. The norm is identical to what we had just done earlier, so it's going to return x times torch.r reciprocal square root x. We're going to exponential square it. We're going to take the average along the last dimension. We're going to keep the dim so our shapes work out, and we're again going to add self.eps. The only difference now is in our forward function, we're not only going to just do output is equal to self.norm, again x.float dot type as x, right, just to make sure it's all the same. We're going to return output times self.weight, right? So we're going to be, we have these weight parameters that will scale the variances and whatnot. So there we go, RMSNorm. So almost identical, we just have this extra weight thing in RMSNorm. So there we go. Now, next up is writing the actual attention mechanism. Now to write attention, we need to do one more thing, and that's the KV caching. So if you remember in neural networks or in these transformer models, KV caching is really just a inference level optimization. And the idea is that you want to avoid recomputing stuff that you've already computed before. And if you basically just go ahead and store this information in the cache. And what that means is, if you don't remember, in KV caching, right, we're going to have a, let's say we have a QK transpose, right? QK transpose. And so that's going to be some, let's ignore the batch dimension. It's going to be some sequence length by embedding dim times transposed embedding dim by sequence. And then that will produce some, sequence by sequence, which we're then going to multiply by our values. And there's a softmax and stuff too, but I'm just simplifying. S by E, and that's going to give us our final S by E output, right? So let's look at the shapes real quick. We have our query is S by E, right? That's a query. And then our key is going to be E by S. And here's the key idea. That's a pun, but here's the main idea. In the case of autoregressive generation, right, we generate one token at a time. So we might pass in a question, a prompt, and it'll look like this. And so we'll use all this stuff, and then at the end, we'll predict the next token, right? Next token. And so what we'll do is concatenate our new token onto the original thing. So this is the one way of doing it. We can take our S by E. This is the same as before, right? S by E. And we'll have our E by S. But we will have concatenated on our new token, right? We've added a new token that we want to predict for, again, the next token. It's autoregressive. So we've generated one token, so we've added it in. It's just that all of this multiplication with this stuff here, and then with the values, a lot of it's repeated. All we care about is how this token is related to all of these tokens here, right? How are they related to all these tokens here? And then again, when we multiply by the values, which is again S by E, and we'll add that new token at the bottom, right? Sorry for the color coding. Again, how is it related to all of these tokens here? Which means that, because again, you can only look at the current and the past, you can't, there's no future in this thing. Which means that all of these keys here and all of these values here can be cached and stored away. We don't need to recompute these keys over and over again. We don't need to recompute these values over and over again. We only need to compute the new key and the new value every single time and just concatenate them on. And then we will just do the attention operation with the new query, because we also don't care about really the past queries to that point. So that's the key idea. We want to understand how this new query is related to the entire history of keys, and then of course the values that we weight against. It's just that we don't want to recompute these keys and values every single time. So why not just store the ones that we already had, because they're going to be the same every time, and then go ahead and produce the new one and concatenate it on. So to do this, there's a lot of ways you can do it. In Huggingface, they have something called the dynamic cache. They have a very fancy version that has all these features. I'm going to write a very dumb one that's will work, right? So it's going to be a cache in it. And this is just going to be our thing that contains our queries and keys caching. The keys and values caching. So we're going to create a self dot, they call it scene tokens. It's going to be 0. It's just a counter. It's going to keep track of how much stuff is in our thing right now. And then we're going to have our, we're going to have our self dot key cache. It's going to be just an empty list of torch.tensor. And remember, this is an attention operation, right? This happens in attention, which means it happens in every single layer in the transformer, right? So every layer will have their own key value cache, right? So we're going to create a tensor, an empty tensor for now, for blank in range config.num hidden layers, right? So however many transformer layers you have, we'll have a key cache for each one of them. And we'll have another one, value cache. We'll have one for each one of those. So there we go. Now that we have our caches, I wrote this quick repr here. I'll just copy it in. This will just print out the, just be a nice way of seeing how many layers we have in this model and how many tokens are currently cached. There we go. And we'll be, when we do it, we're going to write def update self. We're going to pass in some key states, some value states, and our layer value states, and our layer index, right? So what is the key, what is the value, and which transformer layer am I getting these keys and values from? And of course, these will be in the shape of batch by number of heads, by L, by E, right? The standard shape for transformer stuff. If our layer index is 0, right? Because when we do a forward pass, we're going to loop through all the layers. And so only for one of the layers, it doesn't matter which one, but for one of the layers, we just want to iterate our self.scene tokens plus equals 1. So we're going to add, oh, we have a new token. And then what we're going to do is self.key cache. At this specific layer index, we're going to concatenate on torch.cat. We're going to concatenate on our self.key cache at the layer index. So the current one, we're going to take that, and we're going to concatenate on our new states. And we're going to do it along the -2 dimension. So it's going to be along our this dimension, our length dimension, right? We're going to keep adding in one key at a time or one value at a time. And then again, similarly, and that's this operation, right? Literally, I take my sequence length and then I add a new token here, and I take my, or I guess that's the query, but in the keys, we have our sequence length and we add a new token. And then in the next iteration, we'll add another one, dot, dot, dot. So let's keep adding them one at a time. So again, we'll do that for the key and the value and this will be value states. There we go. And we'll return self.keyCache layer index and self.valueCache layer index, right? So there we go. So all we're doing is just adding on a new token and then returning it. So one other method we're going to need is def get sequence length self layer index is 0. I'm only writing this method. We could have also gotten it from our scene tokens, but I'm trying to keep it similar to their implementation. We're going to return self.keyCache layer index for this specific layer index, and typically all the layer indexes will have the same length, right? They all have the same number of tokens that they've processed, but we're just going to grab dot shape -2, right? So we're going to grab the length of the cache in this case, but that only works if self.keyCache layer index dot numl is not equal to 0. Otherwise, it is not equal to 0. Else it's 0. Because if at the beginning, right, our key cache is just an empty tensor. So if there's nothing in there, then it's just 0. But if there's something there, then you can go ahead and take a look at that shape. And that's it. So very simple. It's just a caching mechanism to store all of our cache. So now we can do Llama for text attention and then dot module. All right, so just like always, attention hasn't really changed, so it's going to be same as always. Config layer index super llama for text attention self dot init. There we go. And I'm going to go ahead and just copy this part because no one wants to watch me type this, but I'll just copy it in and we can just talk about it. So it's our config. What layer are we currently on? What's my head dimension? How many attention heads do we have? How many key value groups do we have? So we're doing grouped query attention. So I'll pull up a real quick picture of that. Group query attention. Let's pull up this. I like this picture, so let's take a look at it. Here we go. So multi-head attention is every head of the query interacts with every head of the keys and values. In multi-query attention, every head of the query interacts just one key and value. And in group query attention, we'll have kind of, it's exactly kind of an interpolation between the two. It's kind of, we're grouping them up. In our case, right, we have 40 heads of attention and 8 key value heads, right? Which means what we have is 5 groups, right? There's basically 5 groups of 8 to make the 40, but either way, let's just kind of keep going. We'll probably have to mess with this a little bit, so let's make these, we'll mess with it later. Let's just keep going. We have a scaling factor, just like always. We have our, we also have an attention scale and floor scale. We'll talk, and an attention temperature tuning. We'll talk about what these are a little bit later. Of course, it's a causal model. And then here's one of the key things. The rope embeddings, we actually don't apply them in every single transformer layer. I guess it has to do with the fact that this model is so deep that there's 32 of them. You probably don't need them all of them. So we're doing it on every 4th layer. And that's the key idea. So every 4th layer, we apply rope. Otherwise, we don't apply rope. And then in the smaller model, the Llama4 Scale, they also do an L2 norm on the QK before they actually do the rest of the computation. And so we'll see what that looks like in just a second. So step 1 is let's go ahead and just start writing our forward method. We'll have to come up with some dummy data in just a bit. Forward, self, and we're going to pass in all the usual stuff. So we have our hidden states. We have our position embeddings, right? We have our attention mask. We have our past key values. So these past key value will be the cache, right? That's our cache that we're passing in. Initially, we don't have a cache, so we have to build it. But after it's there, then we start passing it in so we can use the cached keys and values for future predictions. And then our cache position, which is just an index of where are we at. And we'll create all of these things later. You'll see exactly how that works out. But for now, let's just go ahead and set up the basic stuff. We're going to do input shape. Input shape is going to be equal to hidden states.shape. I'm going to ignore the last dimension. So it's everything but the embedding dimension in this case. And then our hidden shape is going to be our input shape -1 self.headDim. Right, so there we go. It's just going to be a dummy dimension for the number of heads, and then we have our head dimension. So there we go. And so now we have our query states. This is just like every other transformer, right? So we're going to do self.QProj. We're going to pass in our hidden states. And like I mentioned, right, every other transformer, we have a QKV, we have an output projection, nothing crazy. We're going to take our hid states, pass it through our queries, and then reshape it to our hidden shape. So let's kind of see what that looks like. So let's create some dummy data. We have our rope embeddings. We're going to hold on to those. These should be fine for now. Let's comment you out. Let's do attention is Llama4 text attention config. Let's go with that for now. And let's do our, for now, I think we are fine. We're gonna have to mess with a little bit of the shapes in a bit. Maybe we should, okay, so while we're not training anything, or we're just inferencing these small models, let's go ahead and just use the defaults, which means our data, so our rand tensor is going to be some batch size by sequence length. Let's use 64 as our sequence length. And our embedding dim is going to be 5120, right? Let's just go with the full tensors for now. There we go. And the position IDs is, let's make this 64. So it's going to be torch.arange 0 to 64. And I think that should work then. So let's take a look, see if this runs. Is there a bug? There's always a bug. Oh, layer index. So we need to tell this that, let's just say your layer 0, right? Layer 0. Okay. Copy a construct. Yeah, we don't need the torch.tensor anymore here. And we can then get rid of you. And we should be golden. Okay, good. Yeah, so we have everything we need, and we'll pass it all in just a bit. So we have our query states. So let's go ahead and do attention. And we're going to first pass in our rand. And let's just set everything here to none just so it doesn't bother us, because we don't really have an attention mask for anything right now. So we're going to set everything to none. Okay. And what we have here is must be a tensor, not a tuple, because we need to pass in hidden states. There we go. And okay, good. So our query states, print query states dot shape. Right, so just like every transformer, it's going to output a batch by sequence length by number of heads. We have 40 heads, and we have 128 per head dim. And we'll repeat this, right, for queries, keys, and values. So we'll have our query states, key states, value states, and that'll be on our Q, K, and B, right? 3 different projections of the exact same data. On our value states, right? So they're all the same shape, right? We're going to go ahead and notice here, key idea, in our queries, we went to number of attention heads. So we had 40 heads of attention. In our keys and values, we only go to 8 heads of attention, because we will be doing the mapping, right? We're going to share these heads of attention with the ones above. So to get that to work, what we're going to do first is dot transpose 1, 2. So we're going to flip our head dimension and our sequence length, just like that. Before we apply any change to our queries and keys, it's time to add our rotary embeddings to them. So again, like I mentioned, when we had done the rotary embedding, we expect our data in the shape of batch by sequence length, right? Basically, we have batch by sequence length by num heads by embed dim, because that's just how it's implemented. We could have obviously done the transpose first and then done it based on that tensor. It doesn't matter. All it changes is basically where we place the none, right? We place the none here because that was where the head dimension was. If we had already transposed it, then the none would be here. Doesn't matter how you do it, as long as you're consistent about it. So there we go. So we have our, let's go ahead and apply our rotary embedding. So if self.use rope. So if this is a layer where we actually want to use the rotary embedding, then let's go ahead and do it. It's going to be query states, and key states is going to be our apply rotary embedding function that we wrote. It's going to take our query states, going to take our key states, and it's going to take our position embeddings .to query states dot device. Now these position embeddings are our, if I can remember, they are the frequencies, right? So again, into our rotary embedding to apply, we need to pass in our frequencies. So let's go ahead and apply them. We computed our frequencies, right? So this is our position embedding is our frequencies. There we go. So let's see if this works, or if there's another bug I get to deal with. Oh wow, it's always shocking when things work. Query states dot shape. Right, so now we have gone ahead and added our rotary embeddings to our queries and keys. Now that we've done that, we can go ahead and do the rest of it. So first of all, I mentioned there's we can pre-normalize our data before we do normalize our queries and keys before we do it. In the smaller Scout model, they do it. In the bigger one, I believe they don't. So we're going to go ahead and do it. So we're going to do if self.qknorm is not none, right? If it's not none, then we're going to do query states is going to be self.qknorm query states, and then key states is equal to self.qknorm key states. So there we go. We have now normalized our queries and keys before we do anything else. And here's one of the key parts. This is a temperature tuning method that they included. So here's the paper that they referenced, and it's actually pretty interesting. This paper is about a scalable softmax implementation. So if we take a look here, scalable softmax is superior for attention. The idea is basically this. In softmax, right, so here's your softmax function. As your number of things get bigger, like if you have a very long context length, because our softmax in attention is happening over the sequence dimension, right? Over the sequence dimension along our, like the softmax operation in the attention computation. So as your sequence length gets longer and longer, the denominator becomes bigger and bigger. And the bigger your denominator becomes, the smaller the overall value becomes. And that's why it starts with the maximum element of a vector output by the softmax function approaches 0 as the input vector size increases, right? So as things get bigger, all the values become very, very small. And the problem is your model will, we refer to as attention fading. The model can't put focus on different tokens because the value that we're using to weight it, saying like, oh, this token is very related to that one, and this token is not that related to that other one. The values we can use to represent those relationships, the interrelationships between words, become very, very, very small. And so they proposed the scalable softmax where you basically have a, here we go, S is some learnable scaling parameter. You multiply our Q by log n, and that seems to work out well. Now, the thing is that comparing this implementation is not exactly what they did in the implementation from Huggingface or the one from Meta when I looked at theirs as well. But here's the reasoning. We're applying temperature tuning to no rope layers where the inference time temperature tuning function is customized to not affect short context while working at very long context. So I'm assuming that they already figured out like a good constant to use for this. Instead of having some learnable S, they just use some constant that they came up with. I'm not sure where this constant came from. If someone does, please do comment below and I'll pin the comment because it's important to know these details. But for now, we're just going to go with it. We're first going to do print cache, our cache position. So our cache position is almost like our cache position is the, where are we? It's basically our position ID. So let's pass that in. Cache position equals position IDs. It's just, you know, what is the position of every token. So they're the same thing. So we can pass that in. So we can again remind ourselves our cache position is just this, right? It's a vector from 0 to number of tokens for every single sample in the batch. And now that we have that, let's go ahead and apply this kind of the scaling on our queries before we keep going. So we're going to do cache position is going to be cache position dot unsqueeze 0 dot expand hidden states dot shape 0 minus 1. I have a feeling we don't need to do this because we already have this in the batch dimension. So I'm assuming our position IDs for the cache position actually is just for one sample. So let's just go ahead and do that. We end up creating the cache position later in the implementation, so I just can't remember off the top of my head. But I think we just need the first one. So let's do that. Let's double check. Okay, yeah, so we end up creating this, basically what we had already. But let's just do it the way it's expected. So we basically end up creating what we already had, but it's fine. So we're good to go. So we have our cache position, and now we're just going to directly apply their formulas. We're going to do if self.attention temperature tuning and not self.use rope. So on the non-rope layers, we're going to go ahead and apply this. So this is going to be attention scales. It's going to be equal to, they do a log of the floor function of the cache position dot float plus 1, and then they divide by 1.0. Actually, no, they divide by self.floor scale, and then they add 1 to that. They multiply it by self.attention scale, and then they add 1 to that. So where they got this from, I'm not totally sure. I'm sure there's a good reason for it. It comes from that paper because that's what they cited. But this is what this stuff is. That's our we have our floor scale and our attention scale and stuff like that. I believe the floor scale is 8192 because our attention chunk size is also 8192. So you'll see later we're going to be doing chunked attention, but for now it's fine. This should be fine for all intents and purposes because we're again not really being able to inference any of this stuff. Now that we have this, we can do attention scales is equal to attention scales dot view, and we're just reshaping it to the shape that we want. It'll be our input shape, and then we're just going to add some 2 dummy dimensions there, just so we can now go ahead and do very simply our, so if we print attention scales dot shape, we'll see that we have our here, and then we added in the extra dimensions for the heads and the embed dim, right? So there we go, and now we set a multiply. So all we have to do is query states is equal to query states times attention scales. And then what they do is they take all of this and just cast it back to the original query states dot dtype. There we go. So again, this is just I'm not 100% positive about exactly where this came from, but it's based on that paper, right? So I'm sure there's some good reason for it. I'm just missing it. So, all right. Now that we have that, we can go ahead. So we already did the transpose on the values. We can go ahead and apply the transpose to our queries and keys as well, because we've added our rotary embeddings and we've gone ahead and done the scaling. So we're going to do query states. It's going to be query states dot transpose 1 2, and this will make it a batch by number of heads by sequence length by embedding them. So the standard shapes that we work with when it comes to transformers. So query states, we have our key states, and here's one of the key parts. We have computed a new query and key. So now it's time to update our cache with this new query and key. So we can do if past key value is not none. Then we can do, and what did I call it? Past key value is not none, right? So if we actually passed in a cache that we want to do it, and we will later on, but for now, key states, value states is equal to past key value dot update key states, value states, and our self dot layer index, right? So here's my new keys, my new values, and here's the layer that I'm on. So go ahead and update my cache, right? Just go ahead and store them in there for future. And now it's time to do grouped query attention. So GQA. So grouped query attention is pretty straightforward. Let me just print this shape thing out real quick. So basically we have a batch by attention heads, and this is 40 right now, by L by E. And then our keys and values are 8. So this is 40. So let's do that, 40. And then each of these are 8, 8, and 8. Which means we need to repeat this 8 dimension 5 times to get it up to 40 so we can do our operation. But it'll be the same 8, right? So it's basically repeating those heads over and over again. So we can write a quick helper function to repeat that KV. So let's do def repeat KV, self, hidden states, and rep is what they called it. So how many repetitions do we want to do? And so our data is just batch by heads, by sequence length, by embed dim is just our hidden states dot shape. And so our hidden states is equal to, we're just going to add an extra dimension in there. We're going to add an extra dimension right here, just none. So this will make it batch by heads by 1 by sequence length. And then we're just going to repeat, right, expand, batch by heads by nrep. We're going to repeat that 1 dimension 5 times in this case, sequence length by our embed dim. And so then we can finally do our hidden states is just our hidden states dot reshape, and we're just going to flatten that dimension. So it's going to be batch by heads times n repetition by sequence length by embed dim. And there we go. So that's just a quick helper function to go ahead and just repeat the head dim enough times to get to the grouped query attention that we want to do. So very simply, we can do our, let's see here. So we need to repeat our keys and values, right? Keys and values up to the 40, and that's by 5. So we can do key state states is equal to self dot repeat KV, right? We're going to repeat our key states self dot num key value groups, right? That's my constant that I made up here. How many key value groups do I have? In this case, it's how many heads do I have divided by how many key value heads do I have, and that ends up being 5, right? So it ends up being 5. And so similarly, our value states, it's going to be self dot repeat KV. We'll do our value states, and again, self dot num key value groups. So I'll repeat them. And so now if we take a look at our key states dot shape, we should see that we go from, now we have 40, right? We had 8 before, but now we have 40. So we've repeated that head multiple times. Now that we've done that, we can go ahead and do the rest of attention. So just like always, our attention weights, right? Attention weights is going to be torch.mapMul. It's going to be the matrix multiplication between our query states and our key states dot transpose. And we're going to transpose 2 and 3 because we want to transpose the these 2 dimensions, right? So it becomes embed dim by sequence length, head dim in this case by sequence length. So we're going to do that. And we're going to multiply it by self.scaling, right? So we have our self.scaling factor, right? Standard stuff. And now we can go ahead and do the rest of it. So first of all, we have our attention mask. So if we have passed in an attention mask, then this is our chance to use it. The way we do the attention mask in this implementation is we use a very large negative number. So in my previous implementations of attention, I just have a 0, 1 mask, and I do the, basically, I fill it with negative infinity. In this case, our mask has negative infinity, or a very large negative number at the positions that we don't want to compute attention. So I can just add my very large negative numbers to my attention weights, and that should be sufficient. So we're going to do if attention mask is not none. We're going to spend a ton of time later building these attention masks, so you'll see that is our attention mask. And we're just going to index it out only for the key states.shape. So we only need to keep our attention mask for however many key value tokens we need that we're attending to, right? So we don't need to keep it anymore. Now you wouldn't really pass in any more than that, but this is just a sanity check basically. Weights dot is equal to our attention weights plus our causal mask. And this causal mask will have negative infinity or some very large negative number at those indexes, at those positions in the attention mask that we don't want to compute attention for, right? Like the causal portion of it. Now that that's done, we just complete attention. So attention weights is going to be nn.functional.softmax attention weights.float dim equals -1 .2 query states.dtype. Right, so we're just going to go ahead, compute softmax on our attention along the last dimension, right? Just like always. And then we're going to go ahead and do our query states there. So that's our attention weights. So then our final attention output is just going to be torch.mapMul. We're going to multiply our attention weights by our value states. So I'll go ahead and do that. And then our final attention output is just going to be attention output dot transpose 1, 2. And we're going to transpose. So if we look at our final attention output dot shape, again, if you're unsure about this, I have a whole video on attention, so you can take a look at it there. But very simply, we're now to batch by sequence by number of heads by embed dim. And so now we can just go ahead and flatten those last 2 dimensions. Dot flatten 2. So that'll go ahead and flatten those. Flatten 2 T's. Go ahead and flatten those. We're back to our 5120 embedding dim that we set above. And now that we have that, we can go ahead and project it in our final output projection. So all the heads get to know each other, right? Nothing new. So attention output is equal to self.oproj output proj attention output turn attention output. So that is our very simple attention implementation, right? Nothing crazy. We added this extra caching mechanism in, right? But other than that, there's really nothing fancy going on here. We also have the grouped query attention, but as you can see, it's just a matter of repeating the key value heads up to your whatever number of heads your original tensor had. Good. Now, up next is our decoder layer. So it's time to start putting all of this together. So we're going to do class Llama4 decoder, or let's call it text decoder layer, nn.module. So we're going to start putting a lot of this stuff together. There's still a lot more to go, but I think we're like almost at the halfway point. The vision part is much simpler, actually, I think, but yeah, this is going to be a long video, which is okay, because this is fun. Layer index, right? So this is a decode, so it's a single transformer block, right? It's going to have an attention mechanism. It's going to have our, in this case, the mixture of experts feed forward layer, but it's just a standard transformer block. And just like always, we need to do super Llama4 text decoder layer self.init. Right, there we go. And so we'll just go ahead and do this. So self.layerIndex is our layer index that we passed in. Our self.hiddenSize is going to be config.hiddenSize. Our self.selfAttention, right? So we'll be using the Llama4 text attention function config, and we'll give it also the layer index for the KV caching. So that's there. Now we have, are we using chunked attention? So we're doing self.use chunked attention. And we haven't talked about chunked attention yet, so we'll get there. Attention is going to be int layer index +1 percent for not equal to 0. So, and every layer that's not divisible by 4, we'll be using chunked attention. On the one where we're doing rope, remember from up here, rope, when it is divisible by 4, we'll be doing not chunked attention, so full attention, or just like standard causal attention. So there we go. We now have our flag for that. We'll be building that in a bit. We have our feed forward, self.feed forward, standard feed forward. It's going to be Llama4 text MoE, MoE that we wrote, config. That'll be our, again, this is the mixture of experts plus the shared weights, the shared weight layer, and then we have two different layer normalizations. So we're going to do self.input layer norm. It's going to be it's going to be the Llama4 text RMSNorm that we wrote with a config.hiddenSize, and EPS is going to be equal to config.RMSNorm EPS, whatever it was set to. And then we'll have another one of these, self.postAttention layer norm, like always. And this is going to be, again, Llama4 text RMSNorm, config.hiddenSize EPS is config.RMSNorm EPS. So there you go. So let's write our forward function. Very simple. We're just going to take all our data. In this case, we're going to pass in our hidden states, right? Our data itself. We're going to pass in our attention mask. We're going to pass in our chunk causal mask. So you'll see what that looks like in a bit. Past key value, that's our cache. We're going to pass in our cache positions, so we know exactly the index of every token. And then we have our position, of course, position embeddings, which will be our frequencies, right, for our rotary embeddings. So let's go ahead, and just like every transformer, we're going to have some residual connections. So let's go ahead and store those residuals. Residual is equal to hidden states, right? Let's store that ahead of time. We're going to first pre-normalize our data before we do our attention computation. So we're going to do hidden states is going to be self.input layer norm. And we're going to do hidden states. And then we're going to do if self.use chunk attention and chunk causal mask is not none. So if we are using our chunk attention, right? So if we're using it in this layer and our causal, and we actually passed in a chunked causal mask, then we can go ahead and set that as our attention mask. We're going to do attention mask is equal to our chunk causal mask. And we'll kind of manage the exceptions around that later on, not just yet. We can now go ahead and compute attention, right? Just standard attention. We can do attention states is equal to self attention, and attention is going to get its hidden states, its position, hidden states. Let's be clear. Hidden states is hidden states. Position embeddings is going to be our position embeddings. Our attention mask is going to be equal to attention mask. Our past key value is going to be equal to our past key value, right? That's our cache. And then our cache position is going to be our cache position. There we go. Once we've computed attention, right, it's time to do a residual connection. So hidden states is going to be residual plus attention states, or attention states, right? So we're going to go ahead and do our residual connection. So that's chunk one, right? We do attention, add to it, and now we're going to make another one. So residual is going to be our attention, or actually it's going to be just the hidden states. We're going to make a new residual, and now we're going to go through our mixture of expert layers, right? So it's going to be hidden states is going to be self.post attention layer norm hidden states. There we go. All right, so we're going to take our data, renormalize it, and now pass it through our feed forward. So again, hidden states is going to be self.feed forward hidden states, and then hidden states is going to be, again, residual, the one that we made, plus hidden states dot, and we have to just make sure residual dot shape because there is a flatten up. So we're just going to reshape it back after the feed forward, because if you remember, after the feed forward, we still have it as a, like these two dimensions are compressed. We still have the batch size and sequence length flattened. We could have unflattened it here. That would have been fine. But this just makes sure that everything is in the correct shape when we do it. Just going to reshape it back to there. Good. So now that we have that, we can return our hidden states. So nothing too complicated, right? Very simple module. And now for the probably the more challenging part, we need to, again, we need to write our full text model, which won't be just one of these layers, but many of them stacked together. We should probably test this though, so let's give this a try. Let's do a Llama decoder layer. We pass in config. What else did you need? The decoder, oh, went too far. Decoder layer, oh, and the layer index, so let's just say it's 0, so that was fine. And we want to pass in our, let's just set everything to none for now. Okay. There we go. Okay. So we have our hidden states. We have everything we need. I think we're good. And we're going to call this layer. Doesn't matter. Okay, let's see if this works. I might have to pass in some more stuff. So these layers are pretty big, so there's actually a lot of effort that goes into them, so this might not be a good idea. Okay, look, it worked fine, there's no problem. But let's go ahead and update now. So we're gonna do, this is where we're gonna simplify our problem a bit. We're going to do, let's see, hidden size is going to be 768. Our intermediate size is going to be, let's do 768 times 4, standard transformer. Let's do our intermediate size MLP is again 768 times 4. And we're going to do num hidden layers is going to be, let's just do 2, right? Let's keep it, because it doesn't matter. It's just stacking them on top of each other. So as long as 2 of them work, then all of them work. We're also going to do num attention heads. Let's do 12 heads of attention. Num key value heads, let's do 3, right? So we'll have 4 groups of 3. And let's add in, I think that's fine for now. So this should be a much more simplified model, which means this can now be 768. No, 768. Sequence length is fine, batch size is fine, which means everything else should be fine. Num, okay, num hidden layers, okay. Good. So it goes a little bit faster, otherwise we'll just be waiting on everything because it's just so big. Or rather than the hidden states, we want to look at the shape of the final output, and we should see batch by sequence by embedding them. So we're good to go, right? That's all of our computations happening right here. Good. Now let's write our text model. So class Llama4 text model nn.module def init self config, and we're just going to pass in everything just like normal. Super Llama4 text model self dot init. Good. So what we're going to do first is just store a couple pieces of information. So self.config is config, self.padding index is padding, or is config dot pad token ID. So what is our what does our tokenizer assign to the pad token ID? So there you go. And then self.vocab size is going to be config.vocab size. So we have that. And so first step is we need to take our tokens and convert them to embeddings, right? Just like always. So we're going to do self.embed tokens. This is going to be nn.embedding. And this embedding is going to have a size of config.vocab size. And it's going to go to a config.hidden size. And our padding tokens don't matter, so we don't need to ever, granted we don't really have any pad tokens in what we're doing, but they don't matter. So there's no point of ever computing gradients on a pad token. So we can do padding index is equal to self.padding index, right? So we're just going to let the embedding matrix know which one of these tokens is the padding token, so they can just ignore it basically. It's just a placeholder. Then we're going to do our layers. So self.layers is equal to nn.module list, right? And we're going to do Llama4 text decoder layer, right? One of the layers that we made. Config with the layer index for layer index in range config.num hidden layers, right? So we're going to loop through layer index from like 0 to however many layers we have, and just create a bunch of these layers. In this case, we're just making 2 of them, right? Just so it goes quicker. And then we just need our last couple things. We need normalization. So self.norm is Llama4 text RMSNorm. It's going to take the hidden size, config.hidden size, and the EPS is again same as before, config.RMSNorm EPS. And then we need our rotary embeddings, right? We need our rotary embeddings to compute those position embeddings that we're passing in. So that's Llama4 text rotary embedding config. So there we go. So let's go ahead and do our forward self. And we're going to pass in 2 options, input IDs. So these are we passing in our tokens? Or we can pass in embeddings directly, and we're actually going to end up using this later, and you'll see why when we do the vision task. Instead of passing in IDs, we're just going to pass in the embeddings. We're still going to be using this embedding matrix. It's just we're going to use it outside of this model rather than inside it. So we're going to do input embeds is none. And everything else is the same. Attention mask is none. Our position IDs is none. Passed key value is none. And again, cache position is none. Just going to pass everything as none. We're going to do if passed key value is none. So if we don't have a cache yet, and I'm going to assume we're always using a cache. In the Huggingface implementation, you can have a cache or not have a cache, is up to you. But if we, I'm just assuming we have one. If we don't pass in a cache, that means we don't have one. And if we don't have one, we have to create one. So we can do pass key value is a cache, right? Self.config. Just go ahead and create a cache, and the cache is initialized as empty, of course. We also need our input embedding. So if input embeds is none, right? So if we pass in input embeddings, then we already have embeddings and we're good to go. So, but if we don't pass in input embeddings, then we need to create them. And to create them, it's very simple. Hidden states is equal to self.embed tokens. We're just going to pass our tokens, input IDs, to our tokens. Otherwise, right, our hidden states is just our input embeds, and that's it. Next up, we need to set up our cache position. So if cache position is none, right, if we don't create one, then we can do our past seen tokens, right? So how many tokens have we seen already in the cache? That's going to be past key values dot get sequence length, right? That method that we wrote up here to get the sequence length, like how much stuff is in there. In the beginning, it's just 0. Otherwise, it's however many things are there. We could have also used the seen tokens flag, right, to do it, but that's fine. So we're going to grab that, and then we're going to do our cache position. It's just going to be torch.arange, from past seen tokens, which will start at 0 at the beginning, to past seen tokens plus hidden states.shape1, right? So how many new tokens are about to come in? So that's my cache position. So the cache position, it basically tells the rotary embedding where am I at? So typically you start at 0, right? But what if you don't start at 0? Let me see if I can find the, maybe I closed it already. That's okay, we can pull it up again. Rotary embedding. Right, if we look at the rotary embedding, remember, we're adding here, or basically multiplying by, our scaling factor. Where'd that figure go? Here we go. Right, where m is 1, 2, 3. M is the position, right? The index position. Now, the cache just assumes that you're starting at 0, because if you're starting empty, then you're starting at 0. But if you are like creating the cache later on, for some reason, I don't know, then you might start at a different index. And so basically the starting index is whatever is inside your cache currently, and then going forward. This way we actually never have to pass in the cache position into our model, because every time we do it, it'll automatically generate from, hey, there's already 15 things inside my key value cache, and I'm generating another like however many things. So that must be the range of what I'm doing, and I can scale my everything for my rotary embeddings accordingly. So again, it's completely up to you, but this just makes life a little bit simpler by just like not having to worry about another thing. Okay. And we want to make sure that this is on the correct device, right? Device is equal to hidden states.device. There we go. Next up, position IDs. If position IDs is none, our position IDs is exactly the same as the cache. It just has the extra batch dimension. That's all. So our position IDs is going to be cache position.unsqueeze 0. So yeah, the position IDs and cache are exactly the same. That's why if you remember, our cache was just, our position ID is just indexed, right? So the position IDs is exactly the same as the cache. It's just a version that has the extra batch dimension for us to broadcast over. But other than that, nothing fancy. So now it's time to do some of the annoying stuff. We need to update our Causal Mask. So we're going to write a method. It's going to be called Causal Mask. Actually, for now, let's not call it return anything. Let's do self.update Causal Mask. And this is where we need to actually compute our causal mask, and that means we're going to pass in the existing mask if we have it. We're going to pass in our hidden states and our cache position. And so let's go ahead and write this method. So first up, create def update causal mask, and we're passing in self, our attention mask, the input tensor that we're dealing with, and our cache position if we have it. There we go. And so for step one is we need to get the sequence length and the attention chunk size. And you'll see why we're chunking a little bit later. But for now, we're going to do sequence length is going to be input tensor dot shape 1. And our attention chunk size is going to be self dot config dot attention chunk size. There we go. And so step one is we need to get the starting position from the cache. Like what index am I at, basically. So we're going to do start cache position. It's just going to be our cache position 0, right? So whatever the first number is where our starting cache position is. If we're starting right at the beginning, then it's 0. If we're later on and our cache is like, we're on the 80th token, then it'd be 80. It's just whatever it is. And we have to do 2 checks now. The first check is we need to make sure that our first cache position is greater than our chunk size. So actually, let's go ahead and talk about chunking now. The attention they do is actually not full attention. So here's the idea. So attention masks always look like this, right? We have a sequence by sequence, right? And typically we delete the top right triangle portion, right? So we're not attending to things that are outside. But what we can do actually is chunk our attention up. So what that means is, honestly, I feel like there's a great figure and it's going to draw it better than I could. So let me just pull up the Llama, the modeling Llama. There's attention. It was, here we go. Yeah. So this is chunked attention. Instead of, so this is a chunk size of 3, for example, right? Chunk size of 3. Instead of computing, so we already aren't doing the top right attention, so that's fine. We can ignore that altogether. But instead of computing how every word is related to every other word, we're going to chunk our text up into chunk sizes of whatever we set. In this case, 3. You can see there's 3 here and then 3 more here. And so that's the chunked attention mask that this model is using. So we're going to go ahead and actually build this chunked attention mask, right? Very simply. How we do it is pretty straightforward. Just a little bit of effort. And it's honestly easier to understand this by just looking at the results. But first off, we need to do our 2 sanity checks. The first check is our cache position, like the starting point of our current token, is it greater than our chunk size, which means we're in the next chunk, right? We're already in the next chunk. So if we take a look here, our chunk size is 8192. We don't really care because that's a huge chunk size and we're not really dealing with that, anything like that when we're just kind of testing this model right now, but we are going to try to build it as close as we can to the original implementation. So check 1 is my starting point greater than the chunk size, which means it's already in the next chunk. So that's going to be conditional 1. It's going to be start cache pause greater than or equal to attention chunk size. That means I'm already in the next chunk. Our second check is the first chunk, like is our first point, our starting cache position, is it in the first chunk? But with the sequence length that we add, will spill over to the second chunk. So we're kind of in the halfway point, right? The first token is in the first chunk and the last token is in the second chunk. So that's our second check. Condition 2 is going to be start cache position is less than attention chunk size. Right, so is the first position less than, so it's in the first chunk, and start cache position greater or plus sequence length, right? So we're adding however many tokens we were adding, how many tokens are we doing, is going for this many tokens greater than our attention chunk size. So that means we're kind of in that halfway point. And so now we're just going to do a very fancy if else. We're going to do key length, right? The length of our keys. And you'll see where we use this. It's going to be torch.where condition 1 attention chunk size plus sequence length minus 1, right? Because it's not right inclusive, minus 1. What is this? This is saying if condition 1 is true, then our key length, right? So if condition 1 is true, so we're more than our chunk size, then our length is whatever the attention chunk size is plus sequence length minus 1, right? Otherwise, right, else torch.where condition 2 is start cache position plus sequence length attention chunk size. So, okay, so again, this seems a little weird. We have like a kind of a nested torch.where happening here, but the idea is very simple. If condition 1 is true, our key length is equal to attention chunk size plus sequence length minus 1. Else, we check for this. Else, if condition 2 is true, then our key length is going to be starting cache plus the sequence length, right? Even though it kind of spills over. And if that's not true, if both of these conditions are false, then it's just the attention chunk size is our key length. And so that's our maximum key length. It's basically whatever we can go up to in this specific chunk, 8192 or whatever it was set to. And so now that we have that, we can go ahead and create our setup for the rest of this. Let's go ahead and do, okay. First up, we need to make a causal mask, right? So causal mask, and this is your standard causal mask, like everything else. So Huggingface loves giving long names to all of their methods, so we're going to do the same. Prepare 4D causal attention mask with cache position, okay? And this is going to take in our attention mask if we have one. It's going to take in our sequence length is equal to our sequence length. How many tokens do we have? What is the cache position we're currently at? Cache position is equal to cache position. Our batch size is equal to our input tensor.shape0. So that's what our current batch size is. Our D type is equal to input tensor.dtype, right? So just to make sure. And then our device is also input device is input tensor.device. There we go. Just a quick setup. So let's go ahead and write this method. I can copy in the arguments, so let's just do that. There you go. So we're writing this method here. And very simply, we're going to do if attention mask is not none, then our causal mask to start with is just the attention mask, right? If we have nothing. Otherwise, right? So otherwise, so if we're passing in a mask, we're already assuming it's correct. But otherwise, if we need to build a mask, which is what we'll do, we will go ahead and create it. So to create it, it's very simple. Like I mentioned, before our mask used to be 0, 1, like 0 for tokens we don't want to compute attention on and 1 for tokens we do want to compute attention on. But now we're going to do a mask of basically negative infinity, like a very big negative number. So we just add the attention mask on and we're done. So we're going to do causal mask is going to be equal to torch.full. It's going to be just like every other one, right? Sequence length by sequence length attention mask. The fill value is going to be our min, so it's going to be torch.finfo_dtype.min. So that's the smallest number possible in this specific, whatever the precision of this d type is. That's our fill value. And let's add in a, there we go. Okay, and then we have the rest of it, right? D type equals D type and device equals device. So we've now gone ahead and created our causal mask. Let's see what that looks like when we do it. So we can do a quick causal mask torch.full. I have a feeling I am missing a, oh no, okay, that's good, yeah. So let's print out our causal mask. Let's make our sequence length very small so we can see it. Let's do 8, let's say. And so this will become 8. And we're testing this on the Llama text model. So let's go ahead and do that. This is going to be now the Llama text model. Into the Llama text model, in our forward method, we have all of this stuff. So our rand is just going to be input embed, I believe. That's what I called it. Input embeds, plural. Okay. And we have a rand, we have our position embeddings. I think everything else is fine. So let's just run this first and see what happens. Okay, so I'm missing a text model config. Doesn't take anything because this is the full text model. Okay. Okay, unexpected keyword, position embeddings. Let's check. Let's see here. We're looking position embeddings, layer. Okay, so because I don't have a position embedding here, let's just look. All I need to pass in right now is my input embeds, and everything else doesn't matter because we create everything else. So let's just get rid of everything else. Okay. Okay, good. So that is our, right? We filled it with negative. It's just, we can see negative something, right? It's just very, very tiny numbers. All right. So we have all of our very small numbers. And now it's time to go ahead and update it. So we need to actually create our causal mask now because we just filled it with our very negative number. So how we do this is we're going to do first, if we have more than one token, right? We only need the causal mask. Like we can't, like a token can't look into the future. That there is only a future if there's multiple tokens, right, to look into. If you only have one token, then it doesn't matter. But we're going to do if sequence length is greater than 1 or not equal to 1. Right, so if it's not equal to 1, then our causal mask is going to be our very standard torch.true, right? True, causal mask and diagonal equals 1. Right, so this is our standard causal mask. Now we'll see that it does the normal right triangle thing. We should do a shorter sequence maybe so it's clearer. Let's try 4. Yeah, there you go. So we have 0 on everything we want to keep and a very negative number on everything we want to get rid of, right? So there we go. That is our causal mask. So when we add this to our attention, then the negatives will make the everything very negative, and then the softmax will zero them out after the fact. So we have that ready to go. Now we just need to do a couple things. So we need to check wherever a sequence index is longer than the cache position. So the idea is that if there's a query before the key value cache index, then that query would have to look into the future, which is not allowed. So we want to make sure that if, I don't know why this would happen, but it could happen. If you have a query for some reason that is just before the key value cache, then that query would have to attend to a future key value, which would break stuff. Now, this wouldn't happen in if you do it correctly, but whatever, we're just going to do it. So causal mask, actually, let's go ahead and do it. Print torch.arange, right? We're going to do arange, and we're going to do sequence length, device equals device. That's fine. And we're going to check where this is greater than our cache position, right? Greater than our cache position dot to device. And we're going to add an extra dimension here, reshape -1, 1. And that'll make sense when you actually see it. Right, so if we take a look, basically it's a true-false flag of exactly what you think. It's another way of creating that right mask, right? But in this case, it's fine, right? So what we're just going to do is our causal mask times equals, we can just multiply by true-false, and there we go. Right, so this is just a sanity check. I feel like we don't even need this, but it's fine. We're trying to keep it close to their implementation. Now, all we need to do, if you remember, our causal mask is currently print causal mask.shape. There we go. Right, it's 4 by 4, but this is sequence by sequence. We need to add an extra dimension for the batch and an extra dimension for the heads to broadcast over. So we just do what we always do. Causal mask is equal to causal mask, none, empty, empty, dot expand. We're going to expand it for the batch size on this one. Leave this one alone, and then these all stay alone as well. Okay? Leave them. And this is going to equal to, right? So now we have our extra dimensions just added in. So we have a batch of 2. We have a dummy dimension for the attention heads, and each head is a 4 by 4 head of attention. And that goes ahead and creates almost our attention mask, but there's one more sanity check. we're going to do if attention mask, actually no, yeah, that's basically it. I think we're good. Attention mask is not none. Yeah, I think this is fine. We actually don't need, this sanity check needs to go away. Let's just fix this. So we're going to do if attention mask is not none, right? We're going to do it right here. Is not none. So if there was an attention mask, we just need to put these two things together. So what we're going to do is a causal mask is a causal mask dot clone. Just going to make a copy of it. And then all we need to do is keep first up to the length in the attention mask. So we're going to do mask length is equal to attention mask dot shape -1. So we're just going to keep if, I don't know why this would happen. To be completely honest, if you just like inference it correctly, then there shouldn't be a problem, but whatever. If you pass an attention mask and for some reason it's a different length, then we only want to keep up to whatever the attention mask has, because the causal mask we create is for the entire sequence length. So our padding mask is then going to be our causal mask. We're going to ignore all the other dimensions, and it's only going to be up to the mask length that we want, right? Basically our key length. And then we have our attention mask. And what we're going to do here is this attention mask, if we pass it in, it's going to have, you know, the dimensions. So we're going to add in some dummy dimensions like this, right? So we, it'll probably come with a batch and sequence length. So we're adding the head and also the sequence length, right? So we end up with batch by head by sequence length dimension dot to device, just to make sure it's in the same place. And so all we need to do now is just check where our padding mask is equal to padding mask is 0, right? 0 means those are the places we wanted to compute attention. And all we're going to do is take our causal mask, and then for these positions up to mask length, we're going to equal it to our, again, causal mask for those specific positions up to the mask length. Dot mask fill, right? We're going to fill it in with the padding values, right? Padding mask with the min d type. Which was this. So long story short, basically if we have an attention mask, all we want to do is copy over the indexes in the attention mask that were to be -infinity, or basically set to 0. We don't want to compute attention on them. We want to copy them into our causal mask as well. Again, these are just like cases that I guess you'd care about if you actually could inference this model, but for now we're not going to bother too much about little details like this, so that's fine. And up next is creating the chunked mask. So okay, so we did step 1. That's our causal mask. So let's go ahead and create that. That's our final causal mask. Up next is our chunked attention mask. So we're going to do, by default, chunked attention mask is none. And we're going to do if sequence length greater than self.config.attention chunk size, right? So if it's longer, then we're going to we have to go ahead and create a chunk mask, right? We only need the chunked mask if we are exceeding the chunk size. So we've gone past 8,100 whatever tokens it was. So we're going to do chunked attention mask is equal to self.create chunked attention mask, right? And very simply, it's going to take self.config.attention chunk size, like what is the chunk size that we want. We'll do a minimal example. We'll do start cache position, where are we starting? End is going to be our start cache position plus the key length, right? So however many keys we're attending to, so there we go. And our device is going to be input tensor.device, just like always. And so let's go ahead and copy the start of this. Here we go. Put it right here maybe. Okay. So we're going to go ahead and create our chunked attention mask. Now to do this, we need to create blocks in the size of the chunks that we want. So let's go ahead and just create an example of this. We're going to do block pause. And I feel like it's easier to explain from what this looks like than trying to explain the math. But basically what we're going to do is create a torch.range from start to end. Let's say 0 to 9. We're making 9 things. And we're going to unsqueeze. And we're going to add a batch dimension or whatever, just an extra dimension. And we will go ahead and divide by attention chunk size. And we're going to subtract this from exactly the same thing, but we're going to unsqueeze on the other dimension so we get every combination of the subtractions, right? So again, the easiest way to just explain this is just by looking at what this block pos looks like. There we go. Okay, so why did you not print out? Oh, let's get rid of this conditional because of course we're not bigger right now. Okay, so we have zeros everywhere. So what we need to do is ABS. Oh yeah, I'm just being dumb because the attention chunk size is still like 8,000 whatever it was. So let's make these 3, right? We're doing chunks of 3. So we're taking a sequence length of 9. Let's do from 0 to 9, from 0 to 9, and we're going to be chunking them into 3. So now it should work. It's just we were dividing by 8,000 something. There we go. This is also not helpful, so we're going to do torch dot block. Let's save. Let's double check this. Okay, here we go. Yeah, so we can see we get our blocks, right? We have our block of 3 here, block of 3 here, block of 3 here, and those are the blocks that we want. And we only want to keep the bottom portion of it because it's a causal mask, right? So we can't look into the future. So that's basically our block detention if we had a sequence length of 9 and we were we had chunks of 3, right? So let's go ahead and put this back. We're going to do start. Actually, let's just keep it going for now. We'll fill in the actual correct things in just a bit. So now that we have that, we can go ahead. This is our block positions, right? So this is where our blocks are. We also need our token positions, and the token positions will basically just tell us what things are future tokens, what things are current tokens. There's 1,000 ways to do this. This is the way that they do it. So is equal to torch.arange. We're going to go from start to end dot unsqueeze 0 minus torch.arange start to end dot unsqueeze 1. We could have also used a right triangle mask to do this, but it's fine. We'll do it how they like it. So there's our final mask, and you can see it's negative, or it's basically 0 or negative in all of our causal positions, and it's positive in all of the non-causal positions. So let's just do exactly what we want. So let's update you. It'll be, actually, let's make you 0 to 9. So it's still the same. And we're going to do 0 to 9 here. So let's take a look at that one more time. You'll have 0 or less in all your causal positions, right? And then positive numbers in all your non-causal positions. So we just need to put these things together. So our final mask is going to be where our block pos is 0, right? Down that kind of area, that center area. And our token pos is less than or equal to 0, right? That's where it's causal. So now we can print out our mask, and we get our final mask, which will look like this, right? It's true in this block, and then true in this block, and then true in this block, and everywhere else is false. So this is our blocked attention mask, and that's basically it. That's the key idea. So now we can go ahead and return our mask. Good. So, and we also want to make sure it's on this correct device. Again, we don't really care, but just so it's correct. And let's go ahead and update all this stuff. So this is actually going to go from start to end, and it's going to divide by attention chunk size. And then similarly, all of these things are going to go from start to end. So start to end, start to end, start to end, and again, we're going to divide by attention chunk size. And this only happens if we've actually exceeded a single chunk, right? Because if we're still within a chunk, then it's just regular causal attention, and we don't need to do anything else. So we have now completed our chunked attention masking. Fun times. Now let's see. So yes, now that this is done, what we can do is our chunked attention mask is equal to chunked attention mask and our attention mask, right? So we want to make sure we get the this mask is only valid wherever the attention mask is valid. Attention mask, right? So only where both of these things are valid. And then because we're doing our attention mechanism, if we print out the chunked attention mask shape. This would not be the shape we want. We need to add in those dummy dimensions and all that stuff. So let's go ahead and do it. So we're going to do chunked attention mask is equal to our chunked attention mask. We're going to add in those two dummy dimensions first for the batch dimension and our head dimension. Everything else stays the same. And then we're going to convert this to our correct dtype, input tensor.dtype. And then we're going to fill it with masked fill, right? We're going to fill all the areas that is true here, right? So whatever's true with our negative infinity, right? So we want to fill them with negative infinity. So it's going to be masked fill, chunked attention mask, torch.finfo input tensor dot dtype, whatever the min is for this specific dtype. And there we go. So we can now return our causal mask and our chunked attention mask. Right, so that's it. That's the attention masking strategy stuff that we have to do. What's next? Now that we've implemented the attention mask in our forward method, we can now return here our causal mask or our chunked attention mask. There we go. All right. So we're making good progress. We're almost done with the language model part of this, which is exciting. So now that we have this, let's go ahead and compute our frequencies for the rotary embeddings. We're going to need that, right? So we're going to do frequency. Frequency is going to be self.rotary embedding on our hidden states and our position IDs, right? Just like that. And just to double check, we only compute our chunked attention mask if the chunk size is there. Yeah, okay, good. So yeah, we'll use that in just a second. So we have our frequency. Frequency is done. And now all we need to do is loop through all of our decoder layers and just get it, just pass it through just like normal. So for layer in self.layers, we're going to do hidden states is equal to layer, and we're going to pass in our hidden states, our attention mask. That's our full attention mask, and our chunked attention mask. Here we go. Our chunked attention mask, if chunked attention mask is not none, right? So in most cases, if our chunk size is small, then we don't really care about all this chunking stuff, right? If our chunk size is small, or if our sequence length is small, and we're within the context of a single chunk, then this will just return none, which means we just want to use the causal mask. Otherwise, we want to use the attention mask, right? So we're going to do our is chunked attention mask if chunked attention mask is not none, else causal mask. And then we can do past key value, our cache positions, and our frequencies. And there we go. If we quickly take a look at our, so these are the layers. These are our Llama text decoder. So we have our attention mask, which is just set to the chunk causal mask if we have it. So there we go. All right. Now that we have completed passing our data through all of these hidden layers, we can now finally do our hidden states is going to be self.norm, hidden states, and we can return finally our hidden states and our past key values, right? We want to get our updated key value, or basically our updated cache, after we've appended this new token to it, right? We always want to keep the newest version of our cache as we're going. So we have now completed our text model, right? So text model. Let's go ahead and give this a test. Let's see if this just works. Otherwise, okay, looks like we have a bug. Attention weight plus causal mask. Let's take a look. Looks like it's not matching in dimensions. Interesting. So we are on line 371. Okay, let's start there. So line 371, this line. So let's check. We can print causal mask.shape and attention weights.shape. Let's just check. Okay, we have this. Oh, this is only 2. Ah, I found the error. Okay. Yeah, so over here, this should be shapes too, right? We only want to keep the sequence length of our keys. And as you can see here, I was indexing 0. It should be, actually it should be 3, right? So it should be 3. We want to index up to the 4th thing because there's 4 things. Okay, there we go. Now it works. All right, when there's so much code going on and you stay up all night working on this stuff, you end up with a couple bugs here and there, but I'll cut them so y'all don't have to suffer through my pain. Okay, so we have here, okay, let's see if I got rid of, yes, got rid of that. Okay, so what we're gonna do now is we've completed computing our causal mask, we've completed our forward method here, and we have this is our text model, we've passed our data through all the layers, and now that we've done that, we can go ahead and wrap it up by, yep, we've normalized our data, and we return everything back. So we are good to go. So finally, we write our last language part at least, Llama4, and this is going to be the actual for causal LM, right? So that's how Huggingface likes to call it, for causal LM. NN.module. Okay, we're gonna, again, just like always, def init self config, and we're gonna do super llama for causal LM self init. And so our self.model is just going to be our llama for text text model that we just wrote earlier with the config. Self.vocab size is the vocab size, and self.lmhead is nn.linear, and it's going to be config.hidden size in, right? And for every single token, we want to predict the next token, so it's going to be config.vocab size, just like that. And this is going to be config.vocab size, right? So it's just adding the additional like language modeling head, right, at the very top. Everything else is the same. So all we need to do is just pass everything through. So def forward self input IDs is none, input embeds is none, our attention mask is none, our position IDs is none, and passed key value is none. And so all we need to do is pass everything in. So our outputs, so we return, right? Our final output for our main model is going to be the hidden states and the cache, right? So we're going to do outputs, and our passed key value, or cache, is going to be self.model. And we're just going to pass in all of the same things, actually. So I'm just going to copy this in. It's fine. Right, we're going to pass in all the same things, all the information that our forward method needed for the language model, and then we go ahead and pass everything through the LM head, right, which will predict, what is the next token, whatever it should be, and we get our final logits and key value. So this should be as simple as just toggling U for U, and we'll get our logits, which we can check here, print logits.shape, and we'll have a bug. Okay, so I spelled something wrong. Passed key values got an maybe I did it singular. Let's check. We have here passed key value. Okay, singular. Let's keep it the same. Pass key value. Pass key value. Okay. Will that fix it? Good. Yeah. So we have a batch size of 2. Each sample has 4 tokens in it, right? Sequence of the 4. And each thing has a possible of 202,048 possible next tokens, right? Whatever it could be. So that goes ahead and wraps up our language model. Now it's time to do the vision one, which the vision one isn't all that difficult. It's pretty similar to a vision transformer. So I'm going to go through it with a little bit faster, I hope. Llama4 Vision MLP. I think yeah. Okay, so we're going to write, so very simple multi-layer perceptron, right? NN.module def init self config. And in this case, right, we're now, our config refers to the vision config, right? So we're now doing the vision model, so we're doing the vision config. So let's go ahead and do that. Super Llama for vision config, or vision MLP self.init. Okay, and this is going to be very simple. It's just going to be, let's update you just to make sure I have this all correct. Okay, good. It's just a simple stack of 2 linear layers with a GLU activation between them, right? Just like the vision transformer. Config, it's going to be config self.activation function is going to be nn.glu. Our self.fc1 is a linear layer that takes config.hidden size, right? It's going to take the hidden size in, and config.intermediate size out, and they do a bias here. Bias is true. And then similarly, we'll do the same thing on the other one. So it'll be fc2. It's going to be a linear layer that goes from intermediate size back down to hidden size. Oh, I deleted that by accident. My bad. There you go. Right, so that's a very, very standard def forward self hidden states. And this is going to be our hidden states is going to be self.fc1 hidden states. Our hidden states is going to be self.activation function hidden states. And again, one more. Hidden states is self.fc2, right? One more layer, and we return our hidden state. So we just pass it through 2 layers with an activation between, standard stuff. Now there is actually 2 MLP layers. I'm not sure why they defined them separately, but they're very similar but slightly different. So we're just going to do them like this. Llama, that's what they call it in the implementation as well. Class Llama or LL Llama4 vision MLP2 is what they call it. So we're going to call it the same thing. Module def init self, and I actually think there might be a bug. I have an issue that I already posted, but I'll put in, basically their in features and out features don't match, but either way, I'll just kind of do it my way here. In features, out features, and config. It doesn't matter for them because they pick the same number for in features and out features, so in the end it's all the same, but just in case you didn't, then it would throw a bug, so I raised that already. Llama4 vision MLP2 self.init. And what we're going to do is, like always, hidden size is config.hidden size. Our self.intermediate size is going to be config.intermediate size. And then 2 linear layers, right? So fc1 is I'll just copy this. I don't want to type all of this out again because nothing changed. We have 2 linear layers from in features to out features, and we actually don't care about this anymore then, right? We specify the in features and out features. So we have in features to out features to out features, just 2 linear layers, and with a GLU activation function and a dropout. And the pattern's the same, right? We pass data through a layer, activation, dropout, pass data through a layer. In this case, we do another activation before we finally return it, or earlier we didn't, but everything else is the same, so nothing crazy. Now, here is a key part of the model, the multimodal projection. So Llama4 multimodal projection. So the idea is that this is a multimodal model, right? So it takes both images and text. And basically all it does for the images is it gets image tokens, right? Because the vision transformer converts the image to a quote unquote sequence, right? Creates an image token. And then it just like concatenates image tokens onto the text tokens, and it's just another thing for the transformer to process, right? It doesn't really care. So in that case, right, we can just go ahead and just do what we want to do. So in this case, we have we need to ensure that the embedding dimension of the images, right, whatever we pick, is the same as the embedding dimension as the text, because we have to concatenate them together. So this is just a layer that projects our images to the same space as the text, right? So it's like an adapter layer basically. So we can do def init self vision config text config. I'm going to pass in both of them, and we'll have super Llama for multimodal projection self dot init. I'm so tired of typing super. Okay. Self dot linear 1 is going to be nn dot linear, and it's going to be our vision config dot projector output dim. So this is in our vision config. I have a vision projection. We haven't written it yet. We'll get there. But I know it's going to output a 4096 embedding. Like that's the embedding size. I know that's going to come out. That's what's going to come out. So I'm going to make sure it's just that. So our vision is going to be at 4096. On the other hand, right? What's the embedding dim of our language? Our vision might be 4096, but our language is 5120. So I need to project one to the other, right? To make sure they're the same, so I can actually concatenate them together. That's all. So we're going to go from vision projector, and then we're going to do our text config dot hidden size, right? Whatever the hidden size we set up was. And they also use a quick bias equals false, right? There's no bias in this layer. Good. So now we can do our def forward self x, which is basically just our images. And all we need to do is just return our things. It's just going to be return self dot linear 1x, and just make sure our images and text are in the same embedding dimension space, right? Okay, next up, PixelShuffle. So class Llama4 Vision PixelShuffle and .module. I will actually create a test for this, a tensor for this, because this one's less obvious about what's going to happen. So let's go ahead and comment yall for now, because we're not touching vision or the text stuff for now. We're going to have our config. It's going to be our Llama4 Vision config. Right? We'll just leave everything as the default for now. In the default, it expects, let's do pixel values is torch.randn, torch.randn. It's going to have, so let's say, a batch size of 4, 3 channels, and expects a 448 by 448 image. 448. So there we go. So let's go ahead and do our, again, self config super Llama4 Vision PixelShuffle self.init. Nice. Okay, so PixelShuffle is very simple. Basically, there's a ratio, and it's how you're moving pixels out of the channel dimension and into the resolution dimension, or vice versa. You can move pixels from the resolution and into the channels. What that means is you're literally taking pixels from the channel dimension and increasing your pixel dimension, or the spatial resolution, or vice versa. You could take pixels out of the spatial resolution and put it into the channel dimension. That's actually what we do in this implementation, because it's controlled by the PixelShuffle ratio. So we're going to do self.PixelShuffle ratio is equal to config.PixelShuffle ratio, which is set to 0.5, and you'll see exactly what that does in just a bit. We'll also have a self.inner dimension is going to be our int. We're gonna compute this in just a bit, so this will make sense again when we get there. We're gonna say this hidden. Actually, we'll do this later. We'll come back to this later. We'll come back to the later part. Yeah. So let's do our PixelShuffle self x, and our forward method. This is gonna be self x. And we can do our shuffled, actually let's just do self.PixelShuffle x. So what we want to do is take this, let's do our, let's do PixelShuffle is going to be Llama4 Vision PixelShuffle. And we want to pass into PixelShuffle our pixel values. So we should print out the x.shape here, and it should work, print x.shape. Oh, it needs the config, of course. And let's actually update this to text config and vision config, just so it's clear. Right, so that's my data, right there. And what I want to do is do some reshaping. So actually, this is not my data. I need to make sure I do this correctly. I have a resolution of 448, and I want, if I remember, I want 16 heads of attention, and I use a patch size of 14. So my resolution, right? If we actually do the operation, let's do print 448 divided by 14. That means I will have 32. So I'm going to have basically 32 by 32 patches, or 1024 patches in total. So that means my data will be, like always, it's going to be batch size by num patches. It's going to be 1024 in this case, because that's what it is. And then our embed dim, which is 768 as defined by this model. Okay, good. So we have that. So this is what we're passing into here. So x.shape should actually be this 4 by 1024 by 768. And this is where we want to do the pixel shuffle. So first of all, if I know it's 1024, I know that I can do this. I can do batch size by num patches by our embed dim. It's going to be x.shape. And what we can do is our patch size is going to be our num patches to the power, right, the square root of it, right, 0.5. Right, I can directly compute my my patch size from here. So, or how many patches I have in each direction. So I have 32 by 32 patches. Each patch is of size 14. So maybe not the best words, but that's fine. And what we want to do is just return our image back to kind of that shape. So we're going to do x is equal to x.reshape, and the batch size stays the same. But we're going to split our num patches into patch size by patch size, and then this can just be -1. So if you look at x.shape, we'll take in that 1024 and split it into 32 by 32, which is cool. Now that we have that, we can go ahead and do our next step. So PixelShuffle, like I said, moves information from the channel dimension to the spatial dimension, or vice versa, right? So how do we do that? We can, let's go ahead and store here, batch size by, let's just do height by width by channels, let's say, it's x.shape. What I want to do is take some of the pixels from this width and move it into the channels, and in order. So how do I do that? We can do x equals x.reshape, right? And we can do batch size by height, right? So we're leaving the batch size and height alone for now. We're going to take the width and we're going to multiply it by our ratio, times pixel, or self.PixelShuffle ratio, which is 0.5. This means we're taking the width, which is 32 right now, and multiplying it by 0.5, so it becomes 16, right? So this will become 16. And then similarly, we're going to take our channels and divide by the self.PixelShuffle ratio. So it's the other way around. So if we look at the shape, we went from a 4 by 32 by 32 by 768, but now we're at 4 by 32 by 16 by 1536. So I've taken every other pixel in my width dimension and I've moved it into the channels. And now we want to do exactly the same thing in the other case, right? For the height. So we're going to transpose these two dimensions and then just repeat this operation again. So we're going to do x is equal to x.transpose 1, 2. And then we can do again exactly this same operation, but this time we're going to leave the width. So the width will be here, right? The width will stay alone. We don't have to touch that. We will then do the height will be exactly the same thing. We're going to multiply it by our PixelShuffle ratio, which means this is now going to be squared, right? Because we've moved the PixelShuffle ratio. We divided once by PixelShuffle ratio. Now we're dividing it a second time by PixelShuffle ratio. So it's squared. So now if we print x.shape, we should see that we have 4 by 16 by 16 by 30, 72. So I've taken basically my 32 by 32 resolution. I have removed a factor of 2 pixels from each dimension, right? Each direction, the height and the width. And I've moved it into here, which is effectively multiplying our original channel dimension or embedding dimension by a factor of 4. And this is very standard PixelShuffle, right? This is used all over the place, but they're using it here. So there we go. Now we need to just put everything back. So right now we have batch by width, by height, by embed dim. We wanted batch by height, by width, by embed dim. Right, we want to make sure our height and width are not changed. So we're going to do x is equal to x dot permute 0, which is batch by height, by width, by 3. So or we could have done a transpose, but that's fine. This is good. And then x equal to x dot reshape, batch size. We're going to flatten all that up again. X dot shape, do -1. And we should see we now have everything back. So we went from 1024 by 768, right? We had 1024 patches by 768 embed dim. And we've converted it to 256 patches by reducing it by a factor of 4 and moving those pixels into the channel dimension, right? And that's basically, that's the key idea of PixelShuffle. And so now we can return X. Nice. So we can call this shuffled is there. Now, what I want to do is this is 3072. So this is my embed dim. I want to project it to the embed dim that I actually want, the projector outer dim that's already set. So we can go ahead and do that. Let's add a linear layer here. So first of all, what is my inner dim? So self.inner dim, well, it's just this, right? It's this formula. It's the channels that came in, the channels I expect, divide by our pixel ratio squared. And the channels in the case is just the embed dim. So this is just really the int config.hidden size divided by self.pixel shuffle ratio squared, right? It's exactly the same thing. We're just doing it here. And our self.output dim is just going to be our config.projector output dim, which means our final is self.mlp is Llama4 Vision MLP2, Llama4. We're not ready for 5 yet. Llama4 Vision MLP2. And this is just going to take our input dim, right? Self.inner dim, self.output dim, and it's going to take the config, right? Just as I defined it. So that's our multi-layer perceptron. And so all we need to do is take the shuffled, pass it through that MLP, and we're good to go. So our projection is going to be self.mlp shuffled. And we can print out, let's just look at it, proj.shape. And we have that, right? So we've projected to the 4096 dimension. So we're good to go. So we can now return proj. All right. Up next, rotary embeddings. One more time. So an interesting thing about the Vision encoder for Llama is it uses both positional encodings and rotary embeddings, which I've never seen before, but maybe if any of y'all know if there's like a paper or some like reasoning for that, go ahead and let me know. But just like before, we need to generate our frequency. Now, this is a little bit different. They do the rotary embedding at the like the image shape, right? Like a height by width. So let's just go ahead and just start, and then I'll maybe draw it if it gets a little confusing. Vision rotary embedding, and then dot module. Okay, so almost the same as before, but just a couple changes because we're working with images instead of, so a 2D image rather than just a 1D like sequence, right? So a couple changes. Super Llama4 Vision rotary embedding self.init. All right, and we're gonna do index is config dot image size divided by config dot patch size. So let's just start looking at this thing as we're going. So for now, let's go ahead and comment all of you out. Oh, let's call this rotary embedding is the Llama4 Vision rotary embedding config. There we go. And let's print out the index, right? So let's see what this looks like. Config not defined because it's called Vision config. There we go. It's 32, which we know, right? Our image size is 448. Our patch size is 14, so there's 32 in each direction. This means our final thing, like our final patches, right, will look like this. We have basically a patch, dot, 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 patch, dot, 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 dot. We have 32 by 32 patches, and each patch is 14 by 14, right? So that's the key idea. So what we want to do is get the rotary embedding for each of these patches. I don't know why they didn't flatten it first and just do the rotary embeddings like they did before. I'm sure there's a good reason for it, because it's images, and so the rotary embeddings aren't as simple as just like, oh, it's just a sequence. There's like a X and Y relationship between it. So that's what we're going to be working on building now. So we're going to be doing our index here. Now what we want is indexes of our X and Y coordinates. So this is pretty easy to do. We can do image index is going to be torch.arange. This obviously assumes our images are square, but that's fine. Index squared dtype equals torch.int32 dot reshape index squared 1. So if we look at our image index, all we've done is just create a vector from 0 to 1023, because there's 1024 patches, right? There's 32 by 32, that's 1024, there's 1024 patches. So all we've done is create a vector from 0 to 1024, and that's it, right? Nothing crazy. What we're going to do now is we need to know, so this is patch 0, this is patch 1, this is patch 2, and this last one will be patch 1024. We need to know the X and Y coordinate of each of these patches, right? That's the key idea. Before we do that though, there's one other small detail that we need to keep in mind, and that's we have a CLS token. So at the end, once we're basically done, right, when we flatten everything together, we'll have like image token 1, we'll have like token 1, token 2, token 3, and these will be the image embeddings. And then we're going to concatenate on a CLS token at the end. So we just have to make sure we do all of that. So for now, our image index, we just need to append on another one. So we're going to do image index is equal to torch.cat, and we're going to concatenate on to this image index a -2. The reason we're using -2 is because we'll be adding one later. And so you could actually pick anything. It doesn't really matter what you pick, but it just has to be some number. So it's just a placeholder. So we're going to do torch.tensor. We're going to put -2 in here. And I just need to add in that batch dimension. So reshape -1, 1. And we want to concatenate on dim equals 0. So let's do print image index. And it's exactly what you think. All we did is add an extra -2 to the bottom. And that's it, right? So that's just a placeholder for where the CLS token is going to be in the future. So we'll come back to that when we actually take a look at it. But first step is we need to get the X and Y coordinates of our data. So again, what I'm trying to do here is this patch here has a coordinate 0, 0. This one here is 0, 1. This one here is 0, 2. How do I get that? Well, the X coordinate is always which column am I on, right? So yes, so 0, 1, 2, 3. So what column am I on? So the easiest way to get that is just doing X coord is going to be our image index, which is from 0 to 1024, and divide by take the modulo with the index. X coord, and that'll give you exactly what we want. It'll basically go from 0 to 32, right? Because how does the X coordinate work? It's going to go 0, 1, 2, 3, dot, 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 up to 31. And then it's going to go again, 0, 1, 2, 3, dot, 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 up to 31. And then again, 0, 1, 2, 3, dot, 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 up to 31. So it's just going to go from 0 to 31 and then repeat every single time. So that's why we can take the modulo with index, which is 32, right? So that'll repeat it every time. Similarly, our Y coordinate is going to be 0 for all of them, and then for the entire first row, and then 1 for the next row, and then 2 for the next row. So all we need to do is just take the integer division by whatever we're currently at, and that will give us what we need. Y coordinate is just going to be our image index, integer division by index. Because as long as we don't get past 31 here, right, it'll round down to 0. Once we hit 32, then 32 divided by 32 is 1, and we're on the next index, right? So that's what we're doing integer division. So that very simply gives me X coord, Y coord. Nothing crazy, just a little bit of manipulation. So we can see it goes, these are our things. And we can see our final tensors are, like we have a 30 here, it doesn't really matter. And we have a -1 here, right? For that -2 that we put there, but we're not going to bother with that just yet. Now we need to get our frequency, right? Basically the same frequency stuff that we did before, and this is going to go exactly the same way. We have our frequency. It's going to be config.hidden size. We're going to divide by config.numAttention heads, and we only need it for half the number of heads, right? Or for half the embedding dimension. So this will compute the head dim, right? What is our dimension for every single head? And we only need this operation for half of them. And you'll see exactly why we need half of them a little bit later. And so our rope frequency is same formula as before. It's going to be 1.0 divided by config.rope data. In this case, the rope is different. They used the standard, I think, 10,000. So rope data torch.arange 0 to frequency dim to 2. And the key idea here is we're only going to keep the first half of them. So we're going to do from frequency dim divided by 2. This is because a little bit later, we're about to interleave and concatenate two things together. So if we take half of them now, then when we concatenate them together, then we'll end up with exactly what we need at the end. So we're going to just take half of them, half our frequencies. And of course, we need to divide. Let's see here. We have .float. I feel like I'm missing a. Let's put you here. There we go. .float divided by frequency dim. There we go. So let's check our rope frequencies. Hopefully they look reasonable. Yep, looks like numbers. And if we look at the shape, it's just 12. That's because currently our head dim, if we check, our head dim, it's 12 right now, and then we'll concatenate them to get them to 24, which is the frequency dim we have, right? So the frequency dim is 24 because we have 48 is our embedding dimension per head. And so we need half, so that's 24. And this is now down to 12 because we're going to concatenate to make it 24. So you'll see that in a second. So now that we have that, we have our frequencies. What we need to do is actually apply our frequencies, right? So what we're going to do is our frequencies x, right, is going to be our x coordinate, and we're going to do +1, right? So the x coordinate and the y coordinate both start at 0, right? The index 0. The index 0 would mean m is 0. We're multiplying our frequency, or we're multiplying our rope frequency by 0. Which means we'd be starting at 0, which would be fine, but we want to leave the 0 part of the 0 frequency, like the very starting point, to the CLS token. So we're just going to get to that later. For now, we have our x coordinate +1. We need to add an extra dimension at the end, just so our shapes match. And so we can check really quick, xcord.shape, and we're going to be multiplying it by our rope frequency.shape, right? These are the things we'll be multiplying together, so we can take a look at them. We have 1025 by 1, and we have 12. So we want to repeat for all 1025 things, these 12 things. So we need to add some extra dimensions to pull this off. So what this is going to be is, we're going to do, we'll get to the +1 later, but for now we can add a extra dimension here, none. So this will just add a single dimension at the end. So it becomes 1025 by 1 by 1. And then to the rope, we're going to add 2 dimensions to the beginning. None, none, and then leave the last one alone. And that makes it 1 by 1 by 12. So this will repeat basically this multiplication operation for every single combination, right? So basically we're going to multiply each one of these positions of the x coordinate by each one of our 12 frequencies. Our frequency dim. So we can go ahead and do that. Our frequency x is then just going to be this times. So it's going to be x cord +1, yes, times our rope frequency. And that gets us almost where we need to be. Let's print out the x. Okay. So, frequencies. So that gets us here, and actually more important is the shape, right? Dot shape. Oops. There you go. All right. So we have a batch by 1 by 12, right? Because we've repeated it. We've multiplied it for all 12 of our frequency for the frequency dim. And now we just need to put it all together. So there's a nice helpful function for this called repeat interleave. So this will basically repeat our data over and over again. So it's easier just to show the result. Repeat interleave. We're going to do it on in chunks of 2, and we're going to do it along the last dimension. And so now you'll end up with 24. So all we did is took our data and just repeated it twice. So if we take a look at our, oops, okay, all we did is take everything and repeat it twice, right? So what's a good way to show this? Let's do 0 maybe? Yeah, so you have 1, 1, 4.6, 4.6, 2. Because it's always the same, right? It's the same values that we're just repeating here. So we've done a repeat interleave, and we're going to do exactly the same thing on the y dimension. So frequency y is going to be our y coordinates. Everything else is the same, right? So we're just repeating these things. Now, what we're going to do, and the reason we repeated them is because we're about to take every other one. So now what we're going to do is take our x and y frequencies, concatenate them together, and then grab every other index. So we have half the frequencies on the x index and the other half on the y index, right? So that's why we doubled them up. So because we're about to grab every other one. So torch.cat frequencies x, frequencies y, and we're going to do dim equals -1, right? We're going to do it along the last dimension. And then we're going to grab every other, so we're going to ignore all other dimensions. But on the last dimension, we're going to grab every other one. So our final frequencies will look like this, right? We'll have 10, 20. So we had 24. It went to 48 when we concatenated them together, but then we took every other one and we're back down to 1024. And that basically goes ahead and covers everything, right? So now it's no longer the same repeat over and over again. We only repeated it just so we could interleave them together, just like this. So we now have all our frequencies ready to go. Now, one sanity check, the last token here is our CLS, right? That's the one that goes with the CLS token. And we want to make sure that for the CLS token, it's 0 frequency. It's a little bit weird because if it's 0 frequency, that means it's at the start. So you would assume that you would put the CLS token at the very beginning, but they decide to put the CLS token at the end. So they append it, but they give it the positional information or the positional frequency information as if it was in the beginning. I'm not sure why, but that's fine. So we're going to do our frequencies is going to be our frequencies dot mask fill image index dot reshape. We're going to reshape it to the right shape, so -111, right? And we're just going to make, this is just adding extra dimensions to make sure everything matches with the embedding dimension and stuff like that. We're going to make sure if it's less than 0, which it is because it's -2 when we set it, right? -2. If it's less than 0, set it to 0. Set everything in there to 0. So finally, our frequencies look like this. Reshape. We just have zeros at the end. So 0 frequency for the CLS token. Okay, good. So now that we have all of that, we can finally do self.frequency sys is equal to, just like before, view as complex. Right? We're going to go ahead and convert these to complex numbers, and we're going to do it by stacking together, torch.stack. Okay, we're going to compute the sine, torch.cosine, right? That's our x, or basically our real part, so frequencies. And then our torch.sine, again, on the frequencies. And we're going to do it on dim equals on the last one. So that goes ahead and computes our complex frequencies for everything else is the same, right? Just computed complex frequencies. And so now we can finally return self.frequency sys. So, or actually, there's no return here. It's the init. So this, again, is a little bit different from what we did. I'm sure there's a good reason for it. But my best guess here is that when it comes to images, you have both coordinates in the x direction and the y direction. Like they're positionally related to each other in two different dimensions. So we need to make sure our rotary embeddings are incorporating frequencies from both directions. So we learn kind of that interrelationship between the two. But either way, that's I think enough. So we can go ahead and do def forward self x, and all this method does is return the frequency embedding. So we're going to do return self dot frequencies, but we're going to just make sure it's on the correct device, right? It's just so, again, it doesn't really matter right now, but now we need to apply these rotary embeddings to our images, right? Embeddings. So let's go ahead and try this. So we're going to apply this to, just like before, our query, key, and frequencies, right? Just like before. What we're going to do is our query is going to be, we have to convert it to a complex number, right? This should be very similar. So we're going to torch.view as complex, right? When convert it to a complex number, we're going to make sure our query is a floating point before we do that. And we're going to reshape it. And this is just like before. We want to expose every other, let's remind ourselves, every other, right? Every chunk of 2. So we're going to expose them by reshaping it to every shape should stay the same, query.shape, everything except for the last dimension. And then the last dimension, we're going to split up into -1 and 2. So that we'll chunk it up into chunks of 2. And then similarly, we'll do exactly the same thing to the key, query, key. Now that we've done that, one thing to keep in mind is our frequency, right? Our frequency information here, and let's check print self.freqsys.shape. Our frequency shape is num patches plus 1 because we have the CLS token, plus by 1, which is a placeholder, and then by 24, half our embedding dim, right? That's what we have. So, or our head dim, right? That's our head dim. And so what we need to do is just add in the extra dimension for the batch, right? We need a batch dimension. There's no batch dimension in this right now. So we can do, we can set this to freaks.unsqueeze 0, right? So we're going to add that batch dimension in. Now that we have that, everything else is the same. We're just going to multiply and just do everything identically. So query out is going to be torch.view as real, or we're going to convert it back to a real number. And we're going to multiply our query by our frequencies. And then we're going to flatten all the dimensions. So basically we have these, we chunked the last 2 dimensions. We want to make sure we unchunk them, right? We're just going to flatten everything after the 3rd dimension, which will flatten this, what we did right here. Just put it back how we found it. So that's our query out. Similarly, we have our key out. So that'll be our key out. Again, exactly the same thing. And then we can return query out dot as, let's just make sure the type is the same, type as query, and our key out dot type as key, just like that. So we now have our rotary embeddings for the vision test. The application of it is obviously very close. It's just how we set up the frequencies, again, was a little different because we have indexes in the x direction and y direction. We wanted to make sure that our rotary embeddings understood that, hey, this patch is close to this, but it's also close to this, right? There's some interrelationship there. And this, I guess, captures that better than just standard positional information. So there we go. Now let's go ahead and do the rest. Now we're kind of in the home stretch. So we're going to first do class Llama4 Vision Attention, right? And then dot module. Okay, so all we need to do is standard. This is just standard attention. There's nothing fancy in here. So we're gonna load in our config, super Llama4 Vision Attention self dot init. Okay, and we're gonna do. I'm just gonna copy this part so I don't have to type it again, but it's literally just basic self-attention, right? We have our QKV and that's it, right? Nothing else, right? QKV proj, and so that means our forward function should also look identical, right? We'll have our hidden states, and we'll have our frequencies, because we also need to do the rotary embedding, right? So let's go ahead and do that. Our input shape is going to be our hidden states dot shape everything but the last dimension, so everything but the embedding dimension. And then our hidden shape is just going to be our input shape -1 self dot head dim, right? Placeholder for the number of heads that we have. And so we can do our query states is equal to self dot q proj, and we're going to pass in our hidden states, and we're going to, actually this shouldn't be hidden states, this should be hidden shapes dot view or reshape hidden shapes, right? Just like that. And we're going to repeat this 3 times, right? Just like always, query key states, value states. We're going to do that with the K. We're going to do U with the V. And that's it, right? And now, very simply, we need to apply rotary embeddings to our queries and keys, just like we did before. So our query states and key states is equal to vision apply rotary embed, the function we wrote. It's going to take on our query states, key states, and the frequencies, right? Everything that we passed in. And now, just like always, we need to transpose our head dimension out of the way, right? We need to make it batch by heads by sequence length by embedding dim, because our head dim is currently the 3rd dimension. So we need to do our query states is equal to query states dot transpose 1 2, and we can again copy U 3 times, query key states, value states, just like that. And then we're going to do attention output is f dot, I just use scale dot product. This is basic attention, right? So there's nothing fancy here. We could have also written it, obviously, but it's fine. We're just going to use that to do our simple attention operation. And then attention output is going to be attention output dot reshape. We want to put it back in the original shape. So input shape -1. That'll go ahead and flatten everything else, except for basically it'll flatten everything else. And then we are good to go. Actually, wait. I think I'm missing a transpose here. Output.shape. Let's verify this. It's always a bug. So let's do, okay, let's do attention is our attention with the config. And into attention, we need to pass in our pixel values, which looks like this. So it's going to be pixel values and our frequencies. So our frequencies is going to be, if we pass into here our pixel values, let's double check. So we pass into here and it just returns our frequencies. So that's our frequencies. And so then we will pass into here also our frequencies. So we have both information. Let's see if that runs. Nope, looks like the mistake. 1024 must match 1025 because we actually haven't added that CLS token on just yet. So I'm going to make that 1025 for now. We'll be adding that CLS token on a little bit later. But for now, this is fine. So we have batch by heads by sequence length by embed dim. So I have to first transpose these actually before I can do any of this. So I need to do tension output. Oh, whoa. Don't delete everything. And tension output is equal to tension output dot transpose 1 2. And so now we can check print attention output dot shape. So yeah, batch by C, and now we can flatten these last 2 dimensions, right? So we can do dot flatten, actually flatten 2, not 3. And we don't need U anymore then. There we go. Standard attention computation, right? Return attention output. Nice. All right, so now that we have our attention done for Llama, now it's time to write the encoder layer, and then a vision encoder, a UnfoldConvolution. That's basically our patch embedding. Okay, just a couple more modules to go, and then we'll finally be done. This video ended up being way longer than I thought it was going to be, but I guess that's my fault. We're trying to do all of this in one go. Llama4 Vision Encoder layer. NN.module. We're going to do super Llama4 Vision encoder layer self.init. Okay, so this is a standard encoder layer. Did I spell this wrong? Oh, def init self config. Okay, so this is a standard, very standard encoder layer, just a attention mechanism, a multi-layer perceptron, and we're done. So this is just going to be a self.hidden size is again hidden size self.self attention is going to be Llama4 Vision attention, and this is going to be config.hidden size. Here we pass in our config, and then again we have self.mlp is equal to Llama4 Vision MLP. Again, we pass in our config, and we then have a self.input layer norm is just nn dot. These are just standard layer normalizations, not the RMSNorm from before. Config.hidden size, and then self.post attention layer norm is going to be again nn.layer norm, and it's going to be config.hidden size, right? Nothing new. So this is standard VIT, right? Standard vision transformer. Forward self hidden states and frequencies. And so just like before, we're going to create a residual of our hidden states, right? And then once we do the residual, we're going to go ahead and normalize our data. Hidden states is going to be self.input layer norm hidden states. That's going to normalize our hidden states. Then we compute attention. So our hidden states is self.self attention, hidden states, our frequencies, right? And then our hidden states is equal to hidden states plus our residual, right? Residual. So residual, that's our residual block. Now we just repeat again. So again, our residual is our hidden states, and then our hidden states is going to be self.post attention layer norm. Right, we're going to go ahead and normalize one more time. Hidden states, and then last two layers, our hidden states is going to be self.mlp hidden states, and then lastly our residual connection. Hidden states is going to be residual plus hidden states. Return hidden states. And there we go. Right? So standard encoder, we have a transformer, we have an attention mechanism, we have a multi-layer perceptron, we add them together. That's it, right? Nothing crazy. So our encoder, our class Llama4 Vision encoder, this will just be a stack of those blocks, right? So we're going to def init self config super Llama4 Vision encoder. Okay. So let's go ahead and do this. To do our vision encoder, it's very simple. It's just self.config is config. Self.layers is nn.module list. And this is just going to be our layer from above, right? This is just going to be our, where'd it go? Right, this is going to be these Llama4 vision layers over and over again. Oh, my VS Code's being weird again. Huh, I don't know why it's not coloring. Let's restart one more time. I am breaking VS Code. All right, whatever. So we have our encoder layer stacked however many times we have it. And so then our simple forward function. Okay, all we need to do, and of course it's forward with x and our frequencies. This is going to be for layer and self.layers. All we need to do is hidden states is our layer, and we just pass in our hidden states and our frequencies. Return. Return hidden states. So very simple. That is our setup for the dot. Okay, that's our setup for the vision encoder. But if you remember, right, every vision transformer has a patch embedding module at the beginning. It's the thing that converts your images to patches to then embeddings. And there's two ways you can do it. You can either use convolutions, or you can use unfold and a linear layer, because when you actually apply a convolution in PyTorch, they're internally using the nn.unfold to use the im to call algorithm. It's all the same thing. So we're just gonna do it the way they did it here. So class Llama4 unfold convolution, right? Whatever. We could have also just done this with the regular convolution, but it's fine. It's totally fine. So self config, and we're gonna do super Llama4 unfold convolution self.init. Okay, and we'll first write self.unfold is going to be nn.unfold, and just like a vision transformer, right, our kernel size is going to be our config.patch size, right? So how big of a patch do you want? And then your stride is also going to be config.patch size, because you don't want overlapping patches. So as you stride over, again, you can go and watch my vision transformer video where I talk about this in some more detail, but you basically don't want overlapping patches. So you just pick a patch size of 14 by 14 in this case, and then you move over 14 at a time, so there's no overlapping pixels between patches. And then our self.linear. So if we have a, so let's say we have 3 input channels, which we do. We have 3 input channels, and each kernel is 4 by 4. That means every patch of this unfold, right? Every patch of pixels is 4 times 4 times 3 pixels. And what we need to do is project this up to the embedding dimension that we want, right? So that's all it is. So our self.linear linear is nn.linear, and it's going to be config.num channels times config.patch size squared, right? So that's how many input pixels are in that one patch of the pixel, right? Because you have 3 channels, and each channel is 4 by 4 or 14 by 14 or whatever you pick for your patch. So this ends up being your patch size, right? The amount of pixels. And we're going to take those pixels and we're going to project them to config.hidden size. And I'll show you an example in just a second of what that does. Bias is false in this projection. That forward self x. So we can now do our unfold. So let's comment all of y'all out. This is going to be unfold is equal to Llama4 unfold convolution config vision config, and we're going to do our unfold and apply it to our pixel value. So we're going to do rand is torch.randn in the shape that we know our data is. So let's say batch size of 4, 3, 448 by 448. Right? That's our picture. So let's go ahead and pass it in, rand. And so what we're going to do is let's do unfolded is equal to self.unfold x print unfolded dot shape. So we are now at 4 by 588 by 1024. Do these numbers feel familiar? Because 588 is, if we check, our patch sizes are 14 by 14, and we have 3 of them. So that's 588. And we have 1024 patches because if you remember again, we did the math, right? We have 32 by 32 patches, right? And each patch is a 14 by 14 by depth of 3 patch, right? That's the patch. So all we're doing is taking it and flattening it out. So really what we have is batch size by number of pixels in every single patch by number of patches, and that's it. Now what we're going to do is transpose these two dimensions and then project the 588 up to the whatever embedding dim that we want. So we'll do unfolded dot transpose -1, -2, right? That'll expose the pixel dimension at the end. And once we have the pixel dimension, we can go ahead and do our projection. It's going to be, we can do x equals self dot linear unfolded print x dot shape, and this should look familiar. Oh, exit. This should look familiar. We have input must be a unfolded, sorry. We have a batch size by our num patches by 768, right? Standard transformer shape. So we're good to go. Return x. That is our unfolding. So now let's just go ahead and put all of this together to create our vision model. And then we can put the vision model together with our language model and we will be done. Llama4 vision. Oh my god, Llama 5. Already want the fifth one before I've even had a chance to play with the first one or fourth one. Def init. Self config. And we're going to do super Llama4 vision model self dot init. There we go. And let's go ahead and do it. So there is a scale parameter that they add, but it's not really relevant to us because we're not training the model. And if we were loading weights, then this wouldn't matter at all. So I'm just going to skip it. So we'll do self.num patches, right? How many patches do we have? We have config.image size divided by config.patch size squared, right? This is how many we have. Patch size squared plus 1 for that extra CLS token, right? So let's go ahead and define our patch embeddings, self.patch embeddings. And this is the interesting part because, actually not this part yet, the positional embeddings is the more interesting part. But for now, the patch embeddings is the Llama4 UnfoldConvolution config. Our self.class embeddings is the CLS token, right? So that's going to be nn.parameter. And let's just do torch.randn config.hidden size, right? It's just a vector of length, hidden size, whatever we want. And then self.positional embedding VLM, the VisionLanguageModel. And this is the interesting part because they have positional information injected into the model, just learnable positional information. But they also have rotary embeddings on top of that. And I'm honestly curious what the gain is of having both of them, or if there's some kind of interaction between the two that I'm missing. Again, if someone knows, just please drop it in the comments because I'm always looking to learn more about this stuff. But either way, regardless, we're just going to go with it. Torch.randn, and we're going to do self.num patches, self. Hidden size, right? Standard positional embeddings. We have how many patches do you have, and what's the hidden size? I feel like my guess here is that they started with the pre-trained vision model maybe, and most vision models are just using learnable embeddings, but just to make the embeddings for the vision part, the vision tokens basically more compatible with the language tokens, they ended up just adding the rotary embedding as well, just so there's some similarity when the transformer's looking at all of these different tokens. That's my guess. I'm not really sure about little details like that, but we have positional embeddings. We also have our rotary embeddings. Rotary embed is going to be Llama4 vision rotary embeddings. Again, config. And we will have a pre and post layer norm. I'm just going to copy this. I'm tired of typing things like this. So let's just put this stuff in. So we have our layer normalizations, and we have our PixelShuffle, which I obviously did not name the correct thing. We have rotary, encoder, convolution. Oh, where did I put PixelShuffle? Were you before? Here we go. It should be PixelShuffle MLP because we do another linear layer afterwards, right? So MLP. Okay, so we have that. So okay, so that's the key idea. We have now our model, the vision encoder that we wrote, and then we have a projection layer that's going to take our learned image embeddings and project them to the dimension that's the same as our language, right? So they're exactly the same then. So now we can do def forward, self, pixel values, and this is going to be pretty much the same as every forward pass. Batch size by num channels by height by width is equal to x or pixel values dot shape, and we're going to do patch embed. Right, first we're going to patch embed. This is just the unfold. It's going to be self dot patch embeddings, and it's going to take in our pixel values, and this will now produce a batch size by num patches by embed dim equals patch embed dot shape, right? That's what that's going to make. And now we need to concatenate on our CLS token. So CLS token is going to be self dot class embeddings, right, that we created. But if we want to concatenate this on, we need to make sure, right now we just have a vector, right? We just have a vector of length, hidden size. We need to add some extra dimensions and then repeat it for the batch size, right? So we need to do dot expand. We want to repeat the first one, batch size number of times, then 1, then embed dim. So this will go ahead and create, it's just repeating our CLS token multiple times for all the samples. And it's a sequence of the 1 because I want to concatenate on this dimension, because right now I have a batch by L by E, that's my images, and now I have a batch by 1 by E CLS token. So I can concatenate these together to make a L plus 1 thing, right? So there we go. So let's go ahead and concatenate that on, and we are post-pending it, right? Appending it, basically. We're putting it at the end. So we're doing the hidden states is going to be torch.cat. It's going to take in the patch embedding module. We're going to put the CLS token at the end, because that's how we did it in the rotary stuff. And then we're going to do it on the sequence dim, so dim equals 1. And because we've added a CLS token to this, our num patches gets 1 extra token, just like that. And now we just need to add our positional information onto hidden states equals hidden states plus self dot positional embedding VLM. So that's me injecting positional information in. I will now do a pre-encoder layer norm. So it's a hidden state equals self dot layer norm pre. And this is going to be our hidden state. And then our frequencies, right? Frequencies is going to be our self.rotary embed on these hidden states, right? That's just going to return our frequencies basically on the same device. And now that we have our frequencies and our hidden states, we can go ahead and pass it to the model. So our output is equal to, or output is equal to self.model, and the model gets the hidden state and it gets the frequencies, just like that. Now that we've passed our data through the model, we will do our post layer norm. So output is equal to self.layer norm post output. Right, I'm going to go ahead and do that. And now we're going to go ahead and cut the CLS token off and do our final vision adapter. So we're going to do our output is equal to output. Let's go ahead across all the batch. We're going to keep everything but the last token, cutting the CLS token off. And then adapted is equal to self.visionAdapter output. And the main purpose, if we kind of take a look here, like why do we do this PixelShuffle stuff to begin with? If we print output.shape and then print adapted.shape, you'll kind of notice immediately kind of why we're doing this. So let's see if we can get this to work. So we have our Llama vision model. That's going to go here, and we're just going to pass in pixel values. So this should probably work. Model. Okay, it'll give us a chance to verify if the model's even working. We have a bug. Exciting. Hidden state. Up here, hidden states. Oh, whoops. I called it X. My bad. Let's see now. What's the next bug? Oh, nice, it worked. Okay, so here's the main benefit. So before we did the vision adapter, we had a batch by num tokens, num patches by 768. But the thing is that if you're, I mean, granted, the context length on these Llama models now are ridiculous, but every word counts. So each of these things eat up a token. And if we know that we want more information in the embedding dimension than in the resolution itself, why not shift some of that information over and reduce the number of tokens you're eating up from the image? So this basically reduces our quote-unquote sequence length to represent an image from 1024 down to 256. And we project it up to 4096, the embed dim, but that's still okay because the embed dim for the LLM itself is just so large that we were going to have to do that anyway. So that's kind of the main gain here. So now we have adapted our thing, and we can return adapted. Nice. So this now completes our the Llama4 vision model. Now, finally, we put it all together. What we're going to do is I'm going to copy this example here, and this example will make a little bit more sense when we actually start doing it. But there's, okay, so this is the part where I would have loved to have actually tested this model. I'm pretty sure it would work, but I'm also sure there's some things that are wrong with it. If y'all do know any errors, please let me know. And I will, and maybe make issues in my GitHub and I can fix it. But what I've done here is I have I've created my Llama text model, right? And here's my Llama vision model, right? So there we go. And I'm going to create a new model called Llama for conditional generation that's going to put both of these things together, and we'll see that in a bit. My input IDs are just random. Again, I don't have any real data, so I'm just going to generate some random tokens, a batch size of 4 by 2048, and I'm randomly generating 200,000, anywhere between 0 and 200,000, because my tokenizer goes up to like 200,000 something. So this is me just generating some random tokens. Now, the way that the tokenizer works is for these vision tasks is that the tokenizer knows, because we know exactly what the output of the image is. We know it's always going to be 256 tokens. It'll always be something like this. Like there's going to be like a start of image, let's call it, I think I call it BOI. So beginning of image token, right? And then there's going to be image token, right? And this will be produced by the tokenizer. Like the tokenizer will do this already. And it'll just be a bunch of these. And there's going to be, in our case, there's 256 image tokens at the end of this, and I know that. And if you just do it, then it won't ever change because the image resolution is always 448 by 448. And so you're going to have 256 of these things, and then you're going to have an end of image token, right? Or something like that, EOI token. And then you'll probably have like a beginning of sentence token, and then you'll have your actual tokens, like from your actual like input sentence that you passed in. But the important part is we have effectively some placeholders in our model for where I'm going to put my image tokens in. And so those are the placeholders that we're going to do. Now, these are the tokens used. So this is the beginning of image token. This is the end of image token. And here, I know there's 256 image tokens that's going to come out of my model. So there's 256 of these image tokens, right? These are just indexes from the dictionary. And what I've done is I've just prepended my image tokens onto my input tokens. This is obviously not exactly the chat template that they're using, but it's fine. It's enough to kind of get an idea of what's going on. So let's go ahead and make it. So we're going to do class Llama4 conditional generation, and then .module. Our final one, thank God, init self. And this is going to get two configs. It's going to get both the vision config and the text config. So we're going to do our vision config, text config, and I'm just going to set some defaults here. So I'm just going to copy this in actually, because I don't want to type these big numbers. There we go. So our vision config, text config, and we have our beginning of index token, end of an index token, and image token index. All of this would have already been in the config itself. So in the Huggingface implementation, they have a text config, a vision config, and then another config that like wraps these two things and then adds some of these additional special tokens onto it. But I didn't bother doing that. So we're just going to pass it in manually here. And so what we're going to do, very simple. First, of course, the last super of the day, conditional generation self.init. Our vision model, right? Self.vision model is going to be our Llama4 vision model, and we're going to pass in our vision config, right? Just like that. And then we have our multimodal projector, right? We need to make sure we take our image embeddings and project them up to the dimension that our language model expects. So that's going to be self.multimodal projector, and that's going to be Llama4 multimodal projector, again, config. And this is going to get both the vision config and the text config, right? Both of them. And then finally, our language model, self.languageModel, is going to be our Llama4 Causal LM text config, right? There we go. So those are all the pieces of our model. And then we just have a couple extra of these things that we just store. So I'll just put it there. It's just so we have access to those variables later. So our input's going to be now input IDs, the pixel values. Let's say it's none by default because you don't have to pass in a picture. The attention mask, also none by default. We have our position IDs, none by default, and past key values, which is also none by default, right? If we haven't created one yet. So there we go. Now, this is why in this method up here, when we created our final model here, here we go. This is why we have input IDs and input embeddings as an option, because what we're going to do now is first embed our text, right? And when we embed our text, we have these extra placeholder tokens ready to go. And then we're going to encode our images and then fill in those spots and then send those embeddings into our language model. So that's the key idea. So this is why we won't be passing input IDs in to our model itself. We'll be passing already embedded tokens. We just kind of have both options. If we didn't have the images, then we could have just passed in the input IDs and it'd be fine. So first, token embeddings. It's going to be self.languageModel, right? We're going to look into our language model, .model.embed tokens, right? And we're going to pass in our input IDs, right? That's going to create our token embeddings. Did I spell this wrong? Llama4 conditional. Okay, there. Okay, so let's start testing. We can print here token embeddings.shape, and let's make the sequence a little bit shorter. Instead of doing 2048, let's do like 64, right? Just so it doesn't take too long. Okay. Okay, so we commented that out. Let's pass into our model. Yeah, so we're going to do our model. We're going to pass in our input IDs and our pixel values, right? Our image pixel values. There we go. We have all that. And so now we can check here in our token embeddings. We can do clear python model.py, and we have ourselves some token embeddings. Yes, 322 makes sense because we're adding all of these extra tokens onto the 64 that's already there. So we actually have, it's probably a good idea to print this out. Print input IDs.shape, right? So there we go. Just so we're extra clear. So our input IDs is 4 by 322. And so each of those 322s were encoded by our token embeddings. But the thing is that we tokenize with some of these like special tokens, right? These image tokens. And if we have an image, we need to take our image tokens and just fill them in. So let's go ahead and do that. So this is the only part of the model that's a little bit challenging again. So we're going to do if pixel values is not none. So we actually have a picture in this case. In which case, if you didn't have a picture, you wouldn't even have to use this method. You could have just used the Causal LM model that we already wrote earlier, but that's fine. If pixel values is not none, what we're going to do is first convert our pixel values to image features. So we're going to do image features is going to be our self.VisionModel, and we're going to pass in our pixel values. So we can print out our image features.shape, and let's take a quick look here. And there we go, right? So we have 4 by 256 by 4096, right? What we're also going to do for now is we're going to just store text embed shape is equal to our token embeddings.shape. we're saving this here right now, the current shape of these token embeddings, so we can return back to them later. But for now, we're gonna do that. Now, what we have here is batch by num image patches by embeddim. Let's just go ahead and flatten them. This will be useful for indexing, and when we use we're actually going to use scatter again, so it's going to be helpful then. So let's go ahead and do that. We're going to do image flat. It's going to be our image features that we created dot reshape reshape -1 by our embedding dim, which was image features dot shape -1. So now we can do image flat dot shape, and you will see that we have 4 by 256 just becomes 1024, and then 4096, of course. So there we go. So now that we have done that, next step is to project these images to the embedding dimension of the actual text, right? In this case, it's 768, right? So that's what we're projecting it to, because we're just doing a dummy small example right now. So we're going to do special image mask, or no, sorry, not yet. Proj image flat is going to be self dot our multimodal projector on the flat images, just like that. And now here's the key idea. We want to look inside of our input IDs, the things we passed in. We want to look inside our input IDs and find out which input IDs are these special image tokens. And in the way I've set it up, there's always basically 256 of them at the beginning, plus the start of image, end of image tokens, of course. So what we're going to do is just check. We're going to do special image mask is going to be equal to our, wherever our input IDs, right? Input IDs is equal to self dot image token index, right? And we can print our special image mask, and we'll see that it's just a true false, right? So it's just going to be, we know the first token is a special, like, beginning of sentence or beginning of image, and then we have lots of trues, right? So everything else after that's true. We'll have 256 trues, then everything will be false after that. So there's our data. We have our special image mask. Now that we have that, what we want to do is go ahead and create, oh, actually, we need to add an extra dimension. So if we look at our, let's put that back, dot shape, let's take a look. You'll see it's just a, what do you call it? It's just a 4 by 322, so it's batch by num tokens, right, including the image tokens. We're just going to add another dimension at the end, and you'll see why we do that in just a bit. So we're going to do dot unsqueeze -1, and this is just going to add another dummy dimension at the end, so no problem there, right? So we have u. Okay, and what we need to do now is just make sure that the device is on the same place, but it doesn't really matter right now. It's going to be our special image mask dot to token embeddings dot device, right? Whatever it may be. So our token embeddings is going to be our token embeddings, the token embeddings that we started with, and we're going to flatten it, right? We're going to flatten it to make it batch by sequence length, batch times sequence length by our embedding dim. So it's -1 by token embeddings dot size -1. We're doing all of this just so we can make the indexing easier later on. So if we look at token embeddings dot shape, we'll see that we have 4 times 322. Oh, it looks like I have a mistake. Tensor object is not callable because this should be, what am I missing? Oh, this should be dot view because we're reshaping it. Oh, dot, not. Okay. There we go. So we flattened the 4 by 322 into basically 1288 image tokens. Oh, sorry, image plus text tokens, and each one's embedded to 768. So that's all of them. But what we need to do is in these 1288, we have these image tokens that we need to fill in. And that's why we just made it like this, so we can create a mask and do that really quickly. So we have our token embeddings, just flattened. And we're going to do final mask 1D is what they call it. It's going to be our final mask. And we're going to squeeze it, right, on the last dimension. And we're going to reshape to -1. And what this is going to do, print final mask 1D, is simply create a simple mask that will do this. It's easier to explain once it pops up. So it's just a true-false mask, right? It tells me, and if we look at the shape, of those 1288 things, right? Of the 1288 tokens, which include image and text tokens, of the 1288, which one of them are images and which one of them are not images, right? So it's just a true-false mask of these are image tokens, these are not image tokens. And it's as simple as that. Our num tokens to fill, this is a sanity check, right? So our num tokens to fill should be 1024, right? It should be 256 tokens per sample, and we have 4 samples. So this should be final mask dot sum. Doesn't really matter. So let's print num tokens to fill. And we'll see that we should have 1024, right? 256 times 4 images that we need to fill in. So this is a sanity check. And we can assert that num tokens to fill is equal to proj image flat dot shape 0, because when we flattened our image, print proj image flat dot shape double equal, right? When we flattened our image, we should have 1024 image patches, each with 768 embedding dim. And we have a total of 1288 or whatever it was, image tokens plus text tokens. And we'll kind of see. So again, just to visualize a little bit about what's going on, just so I'm doubly clear, what we have is, what we've created is basically a, let's say a 1288 or whatever it was by embedding dim thing, right? That's my matrix. But what I know is that this part to like this part is image 1, and then it'll have some like text tokens maybe, and then like this part to this part is the image 2, and each of these are 256 tokens, right? Again, this part to this part, image 3 dot dot dot. That's what we're doing. And what I have here are image embeddings, right? I have image 1 embedding, I have image 2 embedding, dot dot dot. And I just need to copy these embeddings from here, right, that came out of my vision transformer or vision encoder, and stick them in place of whatever was here. Because here we just had some placeholders, right, placeholder tokens. That means I want to take this and stick you here, dot dot dot. So we just want to copy them in. So in the end, we'll end up with a basically like a start of image. You'll have your image, you'll have an end of image, you'll have some actual text tokens, and then you'll have another start of image, and then dot dot dot. And then at the end, we can reshape it back so the batch dimension comes back, right? So we have this. So finally, all we need to do is our expanded mask. Expanded mask is going to be our final mask 1D. We have to expand it because it needs the embed dim as well, just like we did before when we were working with the scatter. So -1, expand -1, token embeddings, and what was it? I think it was just the embedding dot shape -1. So all I did here is just repeat the mask. So print expanded mask. This is just a Boolean of trues and falses, right? So we can see the first token is a false, the entire thing, right? This is the embedding dim, and that's basically what I just drew here. Right? The entire first thing is false because it's not an image token. But then you have a bunch of image tokens. And there you go. Image token. We have an image token. We have another image token. And what I want to do is copy from my actual image embeddings into these corresponding spots. Right? That's basically it. So let's go ahead and do that final part. Very simply, all we need to do is, I scrolled up. Token embeddings is equal, or we can do token embeddings dot masked scatter, right? Mask scatter lets us pass in a mask. What is basically this expanded mask identifies where do I want to copy, like, and where do I not want to copy. And I have my proj image flat, and that will go ahead and copy everything from our flattened projected images into those corresponding things in order, right? So it's going to go straight from top to bottom, which is perfect, right? So it'll just kind of assign individually. Like if we erase this, it'll basically say, oh, this token here goes here, and then this token here goes here, and then this token here goes here, dot, dot, dot. So it'll just do it sequentially for us. So mass scatter. Honestly, these, I feel like most people don't really use these scatter, gather, like these types of operations. They're like really fast, and they are definitely better than doing a for loop. So I'd recommend getting better at them if you're a little bit confused about them. Token embeddings is then equal to token embeddings dot reshape. And we're just going to put it back. This is why we created this text embed shape at the top, because we flattened it just so we can make this indexing easier. But now that we've filled in our image embeddings into our text in those specific locations, now we can just go ahead and return it back to our original shape, token embeddings dot shape. And we'll see now, hopefully it work. There we go, right? 4 by 33, 22 by 768. So we're back to where we started. And once we have done that, we can now take all of these embeddings, right, including the vision embeddings, and pass it to the language model, because they've already trained Llama to understand both image and text embeddings, right, which is really neat. And this is basically how every multimodal language model or multimodal model is working out there. They're basically just concatenating on vision embeddings onto your text embeddings and just giving the whole thing to the transformer, because as far as the transformer is concerned, it doesn't actually care, right? So we have our input embeddings, it's our token embeddings. Our attention mask is attention mask if we pass that in. Our position IDs is the position IDs if we pass that in. And then our past key values is our past key values. And we can finally return our outputs and our past key values, or cache, right? Because that's important to let us speed up inference in the future. So now we can take this, let's make this 2048. And so how this is going to go basically is if we pass in, so I'll just copy this example in. So what we're going to do is take our random data with our random image or whatever, and we're going to pass it to our model, right? And we're going to get some outputs, and we're going to get our cache. And in the first iteration, there's obviously no cache to provide it, right? We don't have cache yet because we haven't done anything, but it's going to output a cache. And this cache is going to include all of the tokens, images, and the keys and values of the image tokens and the text tokens combined, right? Everything's going to be in there. So that's our cache. And then what we're going to do is just do the argmax to get our first predicted token. To get the next predicted token, right? It's typically autoregressive. We're going to pass our new tokens in, right, into our model, along with the cache, and this will go ahead and predict the next token. And this step here should hopefully take less time than this step, right? That's the goal. And so if we just kind of repeat, I don't know, we could repeat this, but it's fine. I'm not really doing a benchmark here. This should give an idea. Hopefully this works. Of course not. Let's see here. What was the bug? We have got an unexpected, let's see. Past key values is not an unexpected thing. So what are we doing here? LLM for causal LM. Oh, I think I kept singular. Maybe I just messed up the, let's see. Wow, can't believe I got that wrong twice. This, I don't know, maybe I changed it and Control-Z'd it. Either way, it needs to be the L, or it needs to be this dimension, right? So it needs to be 0, 1. So either 2 or -2, either one. So there we go. So that's my bad. Kept making that mistake over and over again. But yeah, we only want to keep up to the keys that we're actually attending to, otherwise it's kind of just waste. So, okay, so what we're going to do now is go ahead and run this. And as you can see, we'll basically get a, that's fine, that's our input. We're going to get our, so this first one will take some time. Those are predictive tokens, and the second one goes pretty quickly, right? Because it's already cached. So we can do something like, I don't know, this is obviously just running on the CPU, so it's not that helpful, but CPU inference is important, right? We can just kind of copy this, right? Just copy it a bunch of times. And it'll just keep producing a new token every single time. and you'll get the idea, right? Like the whole point of the KV caching is like, sure, the first input has a bunch of tokens in it. We have 2048 tokens plus our image tokens and all that. But after that, everything should go pretty quickly, right? As you can see. That's the entire point of the KV cache. Either way, that concludes a full re-implementation of the Llama4 architecture. I know this was a lot. It's also a little bit early because I didn't get a chance to make some of those prerequisite videos. So this is, again, more geared towards kind of slightly more advanced people. But I hope you stuck through, you kind of understand what's going on. This architecture is new, and there's still, like as I'm seeing right now, like there's more issues being submitted with some bugs that are in this model. Because my code is directly based off the Huggingface model, if there's bugs there, there's probably some bugs here as well. So if you do find any issues, or if you have answers to any of the questions that I asked through the video, please do drop them in the comment section below. I will try my best to keep this updated. This may not be a fully functional, like, oh, we can inference it, because I just don't have a bunch of H100s lying around, but it does give an opportunity to learn a little bit. So what you should have taken away from this really is you should now better understand what are a mixture of experts. How do we put together a vision model and a language model? How do rotary embeddings work? And rotary embeddings we kind of implemented in a different way in the complex space, which was kind of interesting to learn. I didn't know how to do that before. And that's basically it, right? It's a cool model. Honestly, I wish Meta made a smaller version. I'm sure it's in their pipeline to create like a distilled version of this model so people could actually use it. I'm sure the local Llama people aren't all that happy because I don't know how you could run this in some feasible way. Either way, that'll be it for this one. If you have any questions, drop it in the comment section below, and I will see y'all in the next one.